right, welcome back to the stream. Let's see if the bits are all flowing, but I'm going to try to do another Rust coding stream. I think I made an interesting amount of progress on the same project from last stream, and thought it might be fun. Thought it might be fun to continue on that. Looks like the bits are flowing on live.diode.zone and on YouTube on the scanlime-in-progress channel and twitch.tv/scanlime. I think Twitch is working. Yes. I keep changing the setup every time I stream, but I think it's gradually converging. Luckily, Tuco has decided to join us. Hi. Gotta take advantage of the cat hangouts while they exist. It seemed like he wanted to hang out in here, so I brought in some of his favorite objects. Oh, we also have a a notification bot. If folks want to follow it, it's at scanlime-live on Twitter, and I've got to always make sure to check that that's working. It hasn't broken in a while, but it'll break the minute I stop paying attention to it. So just for a little background on what this actual thing is that I'm going to be working on. I'll talk some more about it later once more folks have had a chance to join, but I feel like it's always useful to kind of introduce things for folks watching the video later. So the whole point of this is I want like a sandbox environment that's easier to use from inside of existing applications that are just deployable wherever. And this kind of... The context is I'm also trying to make a project that's like kind of a video storage backend that could be used to maybe fill in some of the gaps in what something like PeerTube is doing right now, where it doesn't have like a consistent strategy for dealing with redundancy or kind of data representation or transcoding, and so those are all problems I'm pretty interested in solving. So I started this other kind of existing, or this sort of a like an experiment, really. It's I'm hoping going to turn into something that's more like production ready, but right now I'm just trying to do like a proof of concept for how you would do live video ingest in a way that also supports peer-to-peer video distribution. So I'm trying to use IPFS as a data model, make it compatible with IPFS servers for additional video distribution, and kind of ingest and export video in formats that common applications are happy to deal with live. So I want it to be really good at supporting HLS and to be able to natively deal with the same exact HLS formats that software like PeerTube is already using. So I started prototyping something like that, and it's already kind of doing a few things. Like it'll take input video and chunk it up into pieces that are compatible with IPFS, and it'll run a little built-in IPFS server that can talk to both in-browser kind of IPFS streaming clients, which I'm kind of also prototyping alongside this. And it can talk to regular IPFS servers that can be used for redundancy. So part of that project needs the ability to run transcodes in a way that is hopefully containerized a bit, both for security, but also for reproducibility. So when you do a particular video transcode, if I want to store the videos in a system that's content addressed like IPFS, the name that I give those videos depends on the particular bits that are in the video files. So if I want the ability to do fancy things like if I determine during video import that some of the video formats, like maybe it's 360p and 480p and 240p versions or whatever, if I determine that those formats are easy enough to generate at real time that I can treat them as sort of a discardable cache. It's like one of the things that I would like for Diode Zone to save storage space. I would like the ability to generate videos and then regenerate them based on some kind of caching, and the ability to generate them consistently, because they have to have the same contents if they're going to appear under the same name. So I'm still not sure how hard of a problem this really is for media in general. Like I don't know how sort of reliably reproducible all the different transcoders are, But the working assumption I've been going under is that it's possible to make this work pretty well using a system that runs the transcodes under known conditions using known versions of the software. Maybe I need to parameterize it additionally for like the CPU flags, because maybe we determine that there's some like different implementations that FFmpeg uses under the hood that cause different bits in the output. So this might get more complicated, but as a baseline here, it seems like you should be able to take the same input files and the same FFmpeg binary and get the same output. And that I've been trying to use that as a strategy for if I feel like if I can build something for running little containerized real-time transcode pipelines in a convenient way, that'll be useful for solving a bunch of the problems that I find that I need to solve inside of a video server like this. Oh, hello to folks on the Twitch chat. Nice to see folks coming in. The status of this right now, as far as the like container thing that I've been wanting, for my proof of concept video server, I got that working using Podman, which is it's really intended to be a drop-in replacement for Docker that doesn't need to be installed as like a system service, but you can just run it as a normal program as a normal user, which seems like just what I want. It turns out there are some big caveats though, which mean that I can't really just drop drop Podman into whatever unprivileged environment that I have. So it still needs some kind of container runtime, and the way those container runtimes pretty much universally achieve at least the main layer of their privilege isolation is by using kernel namespaces. So that it's like I'm going to say recent because I'm old, but it's been in the kernel for a long time. It's basically the same feature set that allows Docker and several of the earlier generations of containerization solutions, as well as just systemd uses it. So like control groups, namespaces. Those are the basic kernel features that something like Docker uses to isolate a workload inside the container from your outer system. Whoa, hey Tuco, careful. Oh, Tuk. I don't know how we're going to get a good angle on the cat here. So the problem then is that you can't really generally run Docker inside of Docker, because Docker does not allow the same namespace features inside the container that it itself uses to implement the container. So there are various ways around this. The kind of popular solution right now, if you just look for people running containers inside containers, the most popular solution is people will just say, don't do that. You're asking the wrong question. And I understand why they say that, but I feel like this is a pretty good use case for like very lightweight nested containers. I think what a lot of people would have you do is have some kind of external container orchestration infrastructure that you would then hand the keys over to the video server in some kind of limited way. So the video server, which I want to be a fairly low privilege thing, like it should just be a network server that has a little bit of network access and some compute access and not much else. Like I don't want this to be something that is involved in like important application decisions or security decisions or storage of long-term data. It's just like a compute and video moving kind of engine as far as I'm concerned. So I've got this situation where I've got something which is intended to be pretty low privilege. I don't want to add more privileges to this thing just so that I can then put a container inside of it. I don't really want the low privilege, stateless, easy to deploy video server to require like having administrator access to start containers on something. So like the thing that I'm looking for is much more like, what if you're inside a Docker container and you wanted to run like a web page inside the Docker container? You could just run Firefox or Chrome or whatever, and it would have its own sandbox that doesn't use these more high-powered kernel features like namespaces, but does use kind of more universally accessible kernel features like seccomp BPF, as well as a lot of kind of purely user space isolation techniques. So that's kind of more what I'm looking for. I want something that's easy to deploy even in already locked down environments, that doesn't require but the bare minimum kernel features. So just like basic Unix, POSIX stuff plus seccomp BPF, and maybe, a couple of other random Linux extensions that have been around long enough for all the Docker security profiles to support them. Oh, Tuco. I know his face is off camera, but he's just super pretty right now. I think he just wants to hang out. I think he's happy that I brought this scratchy object in here, because he's often annoyed when I'm working somewhere that he does not have a good hangout nearby, because he wants to be nearby, but he doesn't want to be uncomfortable. So now he's just like burying his face in my hand. Well, anyway, maybe it's time to switch to the computer since we don't have a great view of the cat. Cat. Oh, that's a good question. Somebody was wondering about that before, if I'm using the green light as the green screen. Now I have like a spot of paint on the wall that is the actual green screen. It's like green screen paint, but it needs to be lit and it needs very even lighting, or you'll be seeing shadows on the green screen all the time. And I happened to have a light that was linear and could make the green even greener, so I chose that option. But it's certainly not a necessity. Just white light works too, but a lot of folks like green screens with green light just to make the green even greener. Oh, Tuco is so cuddly right now. It's like a shame to work on computers with the cat being super cuddly. All right, so this is what I've got so far. I don't know, my intuition with these open source projects is usually just to like release things immediately, even when they're just like hopelessly broken. But I've also been burned by just like getting people's hopes up with a project that never materializes. So I was working on this for a while, just like on a private Git server. But at some point I decided like, I want to publish this on crates and like, reserve a name for it and like stream it and whatever. And so it seemed worth putting it up on the internet, even though it doesn't actually work yet. But there is a bunch of code there. I feel like I don't know like how much folks on the stream are like operating system nerds, so feel free to ask questions or like request more or less detail if you happen to be catching this live. But I feel like this is very much inspired by especially like user mode Linux, and I feel like gvisor, I don't know how much they'll admit to being inspired by user mode Linux, but I feel like gvisor is basically like user mode Linux rewritten in Go with better security. If folks are unfamiliar with user mode Linux, it is a way, it's not actually a separate project. It's actually just like an architecture that you can compile Linux for. So Linux, the actual kernel, not like the operating system with all of the libraries and everything else, but just the kernel, the actual thing which is properly called Linux. You can just download it and compile it with a bunch of options for a bunch of different architectures. And it has this user mode architecture where it just treats running in user mode on another Linux machine as a system architecture. So it's pretty much what I want in some ways. It's something where you can run this normal user space process as a normal user, and it pretends to be a whole system, kind of like a virtual machine pretends to be a whole system. And just noticing my mic might be a little hot. I don't know if anybody else is picking that up too. So a lot of virtual machines require, like there are a bunch of fuzzy lines between like, oh, what is a virtual machine? What is an emulator? What is a sandbox? Like whatever. People use a bunch of different terminologies to describe the act of making a thing which in some ways behaves like a system and in some ways behaves like an application. But there are a lot of different ways that people go about doing that. Like the most high performance way of doing this that also gives you a lot of isolation is usually to use hardware virtualization these days. So that requires having access to a set of CPU features which let you like save the entire state of the CPU, put that aside, and then go into a different completely separate CPU state and do some stuff, and then switch back to the original CPU state. That's just like the basic primitive that hardware virtualization gives you. I mean, it's gotten more complicated since then, now that we have hardware accelerated memory mapping virtualization and hardware accelerated I/O virtualization. But the basics of CPU hardware accelerated virtualization is just this way of like saving everything and making another one. And it's sort of like a way that the CPU serializes its internal state into a block of memory that you give it and then returns. And while it's in that inner state that's sort of savable and restorable, crucially, it also gives you the ability to set fairly fine-grained traps on CPU behavior. So if the application is doing something that you don't want the CPU to implement in its usual way, you can set up one of these traps at the CPU level such that when one of those things happens, like commonly accessing a hardware I/O port will be like this. So when you're running a virtual machine, you want that virtual machine to mostly run directly on the CPU. But if it starts trying to talk to your hardware, directly, or if it starts trying to talk to regions of memory that would normally be used to access hardware, you want to emulate that stuff. You want to trap the virtual process right there and kind of replace it with some emulation code that you've written that pretends to be the hardware device that it's trying to access. That's just like basically how virtual machines work. And the difference between that and an emulator is just that an emulator is always doing that kind of software emulated thing rather than letting it run on the real hardware. But you can make that line very arbitrarily fuzzy. Like it's just sort of how much of the thing you're passing through to hardware versus how much of the thing that you're implementing in software in a lot of ways. That's why if you look at virtualization software in Linux, like virtualization is usually based on QEMU, which is fundamentally a system emulator. It's just that a system emulator you can hardware accelerate with a bunch of hardware that does that job. So then there are approaches that do that not with an entire system, but with a user space process. So you can run QEMU in that same mode too, where it'll not pretend to be an entire machine, but pretend to be just the user space of a different kind of machine's kernel of the same operating system that you're currently running on. A lot of different ways that you can plug these things together. The way user mode Linux usually runs is you're running a Linux kernel, which is compiled to also be a Linux application. And then that sort of interior Linux kernel can have its own user space applications. There have been a couple of different ways that they historically implemented that boundary between the emulated kernel and the emulated user space applications inside that kernel. And I don't know enough about like the internal details of UML to give you a complete history, but I think for a long time it was based on ptrace, which is a kernel mechanism that's usually used to implement debuggers. It's also what I'm using to do a lot of this. So if you're just like, I bet she's just writing another ptrace jail, I'm going to tune out, then yeah, that's like mostly it. I'm just trying to do it better. I'm just trying to write, yes, it's another ptrace jail, but I'm trying to use some like slightly more modern kernel features, and I'm trying to make it Docker image compatible, and I'm trying to make it a nice, small, easy to use Rust program. So user mode Linux is doing largely the same thing I want to do, where it uses ptrace. I think they also support something which is not ptrace, but I don't know as much about that option. They also had some way of doing it which actually involved sharing some address space between the kernel and the process, which is very not what I want, because that does not a sandbox make. That is not something you can do if you want any kind of security boundary. I think user mode Linux in principle could do a lot of this. It's just that a lot of that code has not been maintained in like a decade because people have moved on. And mostly, I think if people are still using user mode Linux at all these days, the things that they're using it for are like debug and test harnesses for kernel code that does not really get close to the devices at all. So if you're writing a new file system, I've seen people write like file system test harnesses in user mode Linux because you can do that pretty well. It's a good platform for that kind of work. I did try running user mode Linux to do transcodes, but the main limitation I found is that they completely removed multi-core, like multi-threading, multi-processor support from user mode Linux like 8 years ago or something. Um, I don't know the full details, but I think it just never worked well and had a lot of bugs and maybe some security bugs. And so now it's usable. You can run FFmpeg, but it will only be able to use a single core. So if you have a bunch of parallel transcodes, then maybe it's worth just using one core per transcode. But I thought it was worth looking into a more general purpose solution than that. And I also don't trust user mode Linux from a security point of view, really. So then the next best option seemed to be gvisor. And it's still possible that I give up on this and use gvisor. That still seems like it's on the table. But gvisor is fundamentally a user mode Linux-like thing, which is written in Go. It's an internal project that Google started a while ago for running untrusted user workloads on their own internal server infrastructure. So they tried to make it like a really solid security isolation layer. And I think they wanted it to be somewhat easy to use, but it seems like the isolation is like by far the highest priority for this project, which is cool. It might be something that I recommend people use as like an outer container layer for running the entire video server. But I made some attempts at trying to use this as like a nested component inside of like an existing unprivileged Docker container, and it didn't go super well. I was talking about it on Twitter a little bit, and someone else actually filed an issue about this. I'm kind of curious if anybody's made updates on that. And then actually, after somebody filed an issue on this, somebody else made a proof of concept patch. Yeah, so this is the bug, 4371 on gvisor. Yeah, so somebody was like explaining how it works, and then somebody else gives me a proof of concept patch. So yeah, this is actually pretty compelling, and it might be worth going this route. But I'm also a little concerned that the way that proof of concept works is it kind of fundamentally changes the way that the architecture was designed to be layered, it seems. And part of me feels like, well, it would be an interesting and decent project to take that modified version of gvisor and develop it into something that I felt confident in the security of. But it's also just so much more complicated than the thing that I actually need. Like, to just do multimedia transcodes inside of a library, inside of a Rust program, at a strictly lower privilege level, I just need a fundamentally much simpler system. Like, I need some of these bits. Like, I need a little bit of a kernel emulation, and I need a little bit of a ptrace thing, but I don't need any networking, first of all, like none whatsoever. And I need a very small set of Linux APIs compared to what a really general purpose project would need to implement. It's not as simple as I thought it could be. I was originally thinking that it could be more like a system call firewall. There's actually kind of there was like a near miss, something that almost would have made this much simpler. So yeah, it's useful. The canonical list of system calls is in the Linux source code, but there's some like random blogs that put them into an easier to read table, and sometimes it's convenient to use those. So like, this is the interface that we're fundamentally trying to draw security boundaries around, and the building blocks we've got are setcomp and ptrace. So ptrace is a way to kind of remote control another process, and you can you can start and stop it. You can let it execute a single system call or a single instruction. You can run it until it hits a trap that you've set up using setcomp. Those are the kind of things that we're mostly doing. And then setcomp is a way of building really tiny programs. They're not really Turing complete, I think, at least. So this is classic BPF. Linux does actually have a stronger flavor of BPF now, which is used for a lot of like scriptable in-kernel filtering kind of stuff. But setcomp is still using the older flavor of that, which is a much simpler, very, very simple kind of virtual machine that you can write filter programs for. So the way this works is that you'd use setcomp to filter out the vast majority of the system calls, only leaving things that you're sure that you could provide safe access to. And this is a little difference between what I'm trying to do and what gvisor's done, because as the way I understand it, both gvisor and user mode Linux don't pass anything straight through. They emulate everything. because they're trying to be an entire kernel. I am trying to be only as much of a kernel as I need to be. So the way this works, I'm using the real kernel's file objects. So anything that just touches file objects or just touches memory, that gets to be passed through. So, and there's a bunch of this that I need to audit closer. There might be exceptions that I'm completely glossing over now. But the idea is to lock this down so that anything that the sandbox process has direct access to is just file descriptors or mapped pages, not anything that involves the file system, not anything that involves process IDs. Both of those would be virtualized. So for example, if the process was doing a read, I think that's fine because we can lock down which file descriptors they have access to. And just like a normal process, like you can only read from files that you have open. You can't just read from some other process's files. So we would be relying on an existing kernel security boundary that's pretty well established to do that. Open, however, does need to be completely virtualized. So I don't even 100% understand how I'm going to do this. There are some pieces that I haven't totally decided on, but the basic approach that I've got in mind for the file system emulation is that we start with a completely in-memory file system, which is based on read-only mmaps of the container tar files. And I've got that implemented already in this code base. So I've got something which you can just give it a Docker container name, a Docker image name. It pulls it from the registry and checks the SHA hash. And the idea is that this would probably be something pretty small, like FFmpeg or BusyBox or whatever. But it does work on like entire Linux distros. So the idea is it caches the downloaded binary blobs and it caches the decompressed version of those. Because the Docker images do start out as .tar.gz, and it's not really feasible to do random access gzip decompression. So to make any of this performant, you do need to decompress the images ahead of time. So it decompresses them in the cache, and then we've just got these flat tar files, and it doesn't go any further than that on the file system. It just then creates an in-memory representation of the inodes and the metadata and everything else that go along with the container's file system. And the files in that in-memory representation just reference opened mappings of those tar files on disk. So my idea is that somehow we would ask the kind of runtime that still has privileges to access the real file system. We would ask it nicely through some kind of very locked down channel to give us access to a particular file by the virtual path. And so it would do the mapping from virtual path to some kind of real resource, and then return that real resource by passing the file descriptor over a Unix domain socket into the locked down tracer process. And then the locked down tracer process would have to pass the file again through probably a combination of remote syscall execution and Unix domain sockets. It would have to pass that file descriptor to the process that's being traced, and then emulate the return of the system call so that it looks like the emulated system sysopen is just returning that socket that we actually got through, or that file descriptor that we actually got through a domain socket. So that's roughly how open works. I've got a lot of that implemented already. The main question mark I have in my head right now is I don't know what actual file descriptor what file object we use. Since the file object we have in the runtime process is the entire tar file, whereas we want a single file in the tar. And there are a bunch of solutions to this. The easiest and potentially most secure thing is probably just to copy the file and make another anonymous file using memfd create, which is a slightly newer system call that I am relying on in this implementation, which seems to be pretty safe. It's been around long enough that Docker and everything else supports it, and but it's new enough that it has a slightly higher number. This is a pretty old table too, so there are system calls I wish I could use that aren't on this table, but they're also not in Docker, so oh well. Yeah, sysmemfd create. This lets you create just an anonymous file descriptor that refers to nothing on the real file system, just memory, which seems super useful for this, and I'm already using it as part of the bootstrapping process to get the tracer running. But it seems like one way I could do this is to just fully copy the contents of each file in that tar as needed into a memfd like this, and then give the memfd to the emulated process, inside the sandbox. I might end up doing that because I haven't thought of anything better yet. But I don't like that just because it involves this very monolithic cost associated with copying that entire file the first time it's accessed. So you could easily imagine somebody has a container with like an 80 megabyte FFmpeg binary or whatever, and then you want that to start up pretty quickly. And right now it should, like with the design as it stands, because there's one cost that you pay sort of per mapping layer in the Docker image to actually read the Docker image's layer metadata and map it. There's another cost that you pay per file to read the file header and generate metadata information in memory. But there is no cost associated with the size of the files right now, and it would be nice to keep it that way. Whereas if I had to make a full copy of the data in memory, then that would be bad. So I feel like there's probably some way that I can make another file descriptor that acts like a file in sufficient ways, but refers to a mapped subregion of the single tar. But I haven't actually looked through the Linux API enough to see if such a thing exists, or if I'll need to go to Plan B or Plan C. So if something does exist like that, and it can be safely exposed in my seccomp profile, and it's safely supported in all the Docker configurations I care about, then I could do that. If not, maybe I make them MFD. Another option is that I virtualize file pointers as well as file objects. So like the offset that you're at in a file. But that would require interposing on every read or write, which means this whole thing suddenly becomes like a much lower performance wrapper. The architecture that I'm hoping I can hit with this, where I'm interposing on file system operations but not on file objects themselves, means that I/O in this container is just as fast as I/O outside the container or in like a regular Docker or something. Whereas if I start interposing on every read or write, then instead of looking like Docker-style performance, it looks more like user mode Linux performance, which is still probably okay for media transcoding, but is not what I like. It would be nice to have closer to native I/O performance. So that's one thing that I've been struggling with the system call list, is like, how am I actually doing files? I was also for a while thinking that maybe there was a way I could use the real kernel's exec. So for anyone who's unfamiliar with how processes are started on Unix-like operating systems, there is, like, if you start a new process at the shell prompt or whatever, what that would actually do under the hood is first it would fork the shell. So for a brief moment, you would actually have a second copy of the shell. And then the shell process would do the work to set up like parameters and a name for the process that it's trying to run. And then it would use the exec system call to just replace its entire self with that new process. So, right. So what we actually, I don't know what that stub exec ve at is. I think I looked at it briefly, and it doesn't really do much for you other than giving you the ability to specify a file descriptor for the directory you're doing the directory relative to. But I don't know why it says stub in this list. I thought it was actually implemented on x86-64. Anyway, like, the canonical source for all of this is, of course, the Linux source code. So to figure out like what is actually allowed, you pretty much always have to read the source code for stuff like this. The man page has some interesting hints, which I then had to read the source code to verify. Let's take a look at the man page briefly. Oh, yeah. So many forms of exec here. A bunch of these are just user space wrappers for the canonical form of this in the kernel, which is exec VP, or exec VPE, I guess here. The V here means that we're passing an array of parameters instead of using C's variable length argument lists, which is really just like a C standard library thing. But then P means that we're supplying, or sorry, not P. P is not the kernel version. P means that we're searching the path, which is not something the kernel does. That is something that happens in user space. So yeah, I meant exec VE, which isn't even in this list for some reason. I don't know why exec VE gets a different man page. Okay, that's interesting. Is this Linux specific? I think the exec, like this whole family is, okay, so this is POSIX. I thought this was POSIX also. I'm pretty sure this is all just regular, yeah, this is all regular POSIX, but I think they just put that in a separate man page because it's got a bunch of kind of fun Linux specific stuff in there, but maybe man pages are just weird. So yeah, exec VE is the one that the kernel implements directly. It takes the path, the argv, which if you program C, that's like the same exact format as the argv that goes to the main function in C. It's a list of pointers to C strings terminated by a null pointer. The envp is in the same format, but it's key value pairs for the environment variables. And then path name, always, you wish there's an escape hatch for this, right? Like, could I just pass some kind of anonymous object here? Could I just give you a block of memory? Could I give you just like a file descriptor and open that? But this is always a path name. So there is an even less, I don't know if this, I was going to say non-standard, but this might actually be POSIX also. So exec VE at. Is this Linux specific yet? I think this one might be Linux specific. Yes, this is Linux specific. Okay, so exec VE is implemented in the kernel, but internally exec VE then turns around and calls exec VE at, which is basically the same thing, but you can supply additional flags and an additional file descriptor that is the directory you're doing the path name relative to. So it's very similar to open at, if you've come across that system call, which just lets you do a file open as if you were in a different current directory than you currently are. There's a very interesting loophole in here, though. Have you seen it? At empty path flag, right? So there is a way to execute something directly from a file. So I almost used this outside the sandbox. It turns out that there's a library that I'm using to run programs out of just anonymous binary blobs in Rust called Pentacle, which uses the memfd create under the hood. And then to go around and execute those files, what Pentacle does is it uses a fairly common technique of doing an exec on the special file /proc/self/fd, and then your file descriptor number. If you look at these, this is more getting into the weeds on Linux. I don't know how much folks have come across this, but if you're on Linux and you look at /proc, like there's a lot of stuff in there because it's kind of become just like a kitchen sink of random kernel stuff that they wanted to expose to user space as a file. So it's got a bunch of these directories, but mostly what's in there are process IDs, and that's what it gets the name from. So if we look at this shell process, which has a pretty big number, if we look at that, we see a bunch of files. There's also an alias self, which uses the current process ID. And when I say current, I mean that the kernel, as it's performing this file lookup, will use the process ID of the program performing the file lookup to figure out which process to open. So if I were to do something like, ls proc self, this isn't going to fit with the -l. So proc self exe there is user bin ls. If I were to do less proc self status, for example, now you can see the name is less at the top because less is who's actually reading the file. So it gets a little meta. It's a fun way to start poking around inside of slightly more internal parts of Linux. This is actually a useful file because you can see not only the sort of identity and state of the process, but you can see like what's the parent of this process, who's got ptrace attached to it, which becomes useful later. How many file descriptors does it have? So useful things if you're trying to do kind of low-level remote control of a process. I keep doing something that highlights the entire buffer accidentally. I am running the terminal inside Emacs. Don't get mad at me. Maps. So there are a couple different ways to access this, but this will be super useful. This maps file, it's one line per memory mapping, and then these are address ranges. So you can see that all the pointers between this address and this address in this process are actually backed by this object in the file system. And it tells you the offset into that object. I think that's the size of the object, and the mapping permissions. I forget what these are. I think that's related to the type, but I'm not sure. So this is showing us like the actual program mapped in several pieces. Each of these lines corresponds to one section in the program's binary. So one of the elf sections in the elf file in this case. We can see like there's a heap, there's a stack. It might not always know what's the heap and the stack. These are kind of the kernel's guesses, I think, or rather like the initial values. But depending on what your program is doing, it might have just like mapped some anonymous memory to use as a stack or whatever. The permissions are a bit more of a hint. So you can see here, like this is an executable code segment. So, nowadays people mostly don't allow code execution from random memory. So only the sections here that actually have code are marked X. Likewise, a lot of these are read-only. But the read-write memory are things like the stack and shared global data in the C library. That's a little weird. I don't know what that actually is. So yeah, we could dive deeper and figure out what all these actual mappings are. I'm sure we'll need to do that later. But I was going to talk about proc self fd. These are all the file descriptors that you currently have open. And if the thing is actually something you can link to, it'll have a link. A lot of things, if you have like a socket open, for example, it'll have a link to an object that isn't actually a real file, that doesn't actually dereference, but it tries to kind of annotate that at least. So what's a better example? Like what if this ls had some additional file descriptors? So what if I wanted to open file descriptor 42 and attach it to dev null? Is that not how that works? Yeah, there we go. I always get the order of that wrong. So that just runs ls. So these are still ls's files, but I've just attached this new file descriptor to a particular place. So that's kind of the stuff you can do here. And then you can actually, if you have a file descriptor attached to a process, you can just exec that node. And the kernel even has some specific support for it, so it doesn't like accidentally close that file descriptor at the wrong place. So like this seems to be something that is like not an extremely esoteric technique. So execve lets you do that without anything special. The problem with something like that is I just can't allow the sandbox to call execve because of that file name argument. There's no safe way with seccomp to allow file descriptor or system calls with only certain strings and not other strings. And that's just because of how strings work in system calls. Like the string isn't actually part of the system call. System calls they're like regular function calls, right? But they have to have a very restrictive format because the machinery that's used to kind of marshal and unmarshal the arguments for system calls has to be very simple so that it can run fast and it can be implemented at a very low level. Or at least that's the way things were when Linux was originally written. Maybe you do things more differently if you were starting an operating system completely from scratch. But the way Linux does this, system calls take up to 6 kind of untyped machine word-sized parameters that they can just do whatever with. So you can't actually pass a string to open. You pass a pointer to a string to open, and then inside the kernel, open will map some memory out of your process to read that string, and then it'll know what the string is. The problem with that is the setcomp filters. Even though you can actually read the value of the parameters in the setcomp filter, you can't map the memory. You can't read the memory. Even if you could read the memory, and I mean, there are ways around that part. Like you could have a separate process like this ptracer. The ptracer could have a mode where it stops and examines every exec system call, checks to see if the file is fine, and if so, it passes it to the real kernel. If not, it just aborts it. But that wouldn't actually work. There would be ways to defeat that pretty easily. For example, you could have another thread in that same process that, in a really tight loop, is trying to rewrite that file name with a different file name that isn't safe, and kind of adjusting the timing of that write back and forth. And if you repeat that process often enough, you could get that other thread to race with the kernel, and the filter, wherever it's implemented in setcomp or in ptrace, wherever, the filter could read that string and decide it's fine, and then that malicious thread that's racing your filter would rewrite the file name, and then when the real kernel exec reads it again, it's malicious, and now you've just run a binary you shouldn't. So that's called a time of check, time of use vulnerability, and it's kind of a classic reason why you can't do safe things with strings in ptrace jails like this, really. So there's sort of a rule you can make for yourself in doing projects like this, where if something involves a string, you can't do any kind of like checking it and then passing it through to the real kernel. You have to emulate it entirely if there's a string involved. Luckily, there aren't that many strings that are involved in the kernel, but like the ones that are mostly like buffers that you're reading or writing somewhere, or well, so I should be clear, actually, strings and buffers are actually a little different, because like the data that we're reading and writing with like a write system call, I'm pretty sure that's totally safe in this context. The kernel doesn't interpret that data at all. It's acting as a conduit to pass it to or from the file. And then the file is something which the process in the sandbox does actually legitimately logically own. So that seems fine. But I guess what I mean is like strings that are interpreted as arguments by the kernel are never safe to pass through like this because we can't verify them safely. The other reason that the read and write case works is that we never look at those blocks of data in the tracer. If we were inspecting those blocks of data in the tracer for any reason, that inspection would be subject to a race condition for the same reason. So that might be something to worry about if we're starting to do weird things with read and write to implement file pointers strangely, but that's also one of the reasons I'd like to not have to interpose on read and write. I'm a little behind on chat here, but I'm going to try to catch up in a minute. My intent here is not to make people lost, but I'm just trying to like, I'm trying to describe the project, but if there are like opportunities to describe things at a different level of detail, I'm happy to try that also. Also, like, I'm kind of a virtualization nerd. Like, I've been doing operating systems-y stuff for a long time, and so this is kind of like my bread and butter, so don't feel bad if this is like a little esoteric or weird. It's intended to be esoteric and weird. I feel like this is knowledge that more people need to have, but it's certainly not super common right now. Oh no, we have a follower buying bot. Let me nuke that real quick. Oh, are they already gone? There we go. Sorry, I'm still new at Twitch. Okay. So we were talking about files, talking about exec, talking about strings being unsafe. There's a, whoops. I just accidentally reloaded Twitch because I had the keyboard on the wrong computer. I'm hoping that didn't break anything. I think we're good, but I might have missed any chat messages if you said anything in the last, like, 30 seconds. Sorry. Okay. Let's see. Yeah, this was almost great. So exec ve at the Linux specific version of exec, it does actually have this option, at empty path. If path name is an empty string, operate on the file referred to by dirfd, which may have been obtained using open. Oh, that's interesting too. I didn't actually notice that parenthetical, and now I'm even more confused. Why would we be operating on a file that was opened as a path? I might have to read some more source code to figure out what that even means. Normally, if you open, so like file descriptors in the kernel, they normally refer to like normal files, right? But there are a bunch of things that they could refer to that are a little more esoteric. I mean, a lot of people are used to like Unix sockets and Unix pipes. But if the file was opened to refer to a directory, you can use that file descriptor as like a base for additional file lookups. You can also read the directory to determine just like which files are in it, but that uses a separate way of reading the directory. It's not like a normal read. So this is a little weird. I didn't entirely look to see what the restrictions are around this particular file descriptor, but I read enough Linux source code to convince me that there's no secure way to use this inside of seccomp, because if it was written such that at empty path flag was always, like if that flag always meant that the path was treated as, if that always meant the path was ignored, basically, that would be the only safe way to do this. So if that flag always superseded the contents of that path name string. But that's not how the kernel implements this, it's the opposite. So in fact, the path name could always supersede that at empty path string, which means that someone could race your empty string with a non-empty string and open a random file in the system, which would not be a sandbox. I would add that to the list of things that would not make this a sandbox. So yeah, I don't think there's any way we can use the kernel's actual exec, which is not a big deal. I mean, it seems like a semi-useful security boundary to not use the real kernel's exec. Even if there was a way to use it securely, it seems like it would be a useful hardening measure to be doing the binary parsing ourselves rather than handing it to the kernel in any capacity. So I'm not super distraught about that, but it's a little annoying. So I think what our exec is actually going to look like is more like going through and manually unmapping all the memory and unmapping all the files and everything else from the process. Basically doing the same things that Linux does when it internally implements exec, but doing them in user space over a ptrace channel. So that means we have to be able to do some fairly complicated things in the context of the process that we're running in the sandbox, but controlled by the tracer process. So that's kind of where I'm at right now in implementing this. I'm trying to get that part working. I need to have a way to do I need to have a way to open the file, probably the same as opening any other normal file. And then Sorry, I need to take a quick audio check. Okay, I think that's fine. My last stream, I was concerning myself with this noise I was hearing in the headphones for a while, but sorry, I know that doesn't help. But it turns out my headphone wire is just starting to die. So yeah, I'm trying to do some somewhat esoteric things in the context of the tracee process. The two places this has come up so far is in loading processes. So I need to be able to execute mmap and munmap operations in the context of the traced process. I also need to be able to receive file descriptors from a socket so that I can pass the results of things like open into the traced process. So yeah, that'll be a little weird. ptrace kind of lets you run system calls in the context of the process you're tracing. I'm still kind of trying to get that working properly, though. I've got it so that I can run one system call, and then my second system call is broken because something gets stuck in the wrong state. This is also kind of complicated because you have to have somewhere to put your temporary memory. So if you want to read a file descriptor from a socket, a lot of that is just system calls, but you do actually need a buffer to receive the file descriptor into. There's like a cmessage header buffer that you have to create. So I think it's safe to make that on the stack, but that might be complicated. There might be edge cases where that breaks. So some portion of that job involves figuring out where there is a safe stack zone to put temporary arguments. Making sure that the temporary arguments are not used for anything security critical, because anything we put in the guest's address space, I'm calling it a guest because I'm used to virtualization, but anything we put inside the tracee's address space is not trusted because the tracee can use another thread to race us in accessing that data. So it's fine, for example, for receiving a system or receiving a file descriptor, because like the worst it could do is receive the file descriptor incorrectly. Like it could corrupt the internal state that's used by our emulated open, and it would break its own access to file descriptors, which wouldn't really cause any problems for anything else. So like those are the kinds of security concerns and decisions that we'll have to make in that part of the emulation. Catching up on chat a little more. Am I saying that there's a potential arbitrary file read or execute vulnerability? I'm not sure what the context was when that question was asked, but if you mean if I tried to restrict execve or execve-at using only ptrace or setcomp without emulating the loader, then yes, there would be an arbitrary file exec vulnerability that I would not be able to patch. That would mean that there would be a way, if you wrote code inside the sandbox that raced the parameters for the exec system call, you could get the code inside the sandbox to exec an arbitrary process outside the sandbox. And there are probably ways to, you could just call a shell, right? Like you could call a shell with arbitrary parameters and you have full access to the outside of the sandbox. There also might be ways that you could turn that into a file read using some kind of like more esoteric technique. But you could also just call a shell and get the shell to read your file. So yeah, it wouldn't even be that hard to trigger, right? It's just a system call race condition. It might be something that requires a bunch of tries to hit the right timing window, but there's no way to protect against it without making your container like single threaded effectively. And that's, I think, basically how user mode Linux solves that problem. But I think they're solving a slightly different problem, but I think that might be similar to the reason why user mode Linux had to ditch their multi-threading support. Okay, yeah, that was the time of check time of use vulnerability. And then there's a question from Twitch chat about whether I could call brk, which is the system call that's usually used for allocating heap memory, and then use that new space until the underlying program calls brk, and then move the buffer. Oh, I see. For the in the context of having a temporary buffer. Um, that is certainly possible, yes. I could put it basically at the end of the guest's emulated heap. Um, that is actually even harder to get right for multi-threading than to just put it on the stack, though, because that means that if another thread does a memory allocation, then that memory allocation could just at any time start to overwrite the buffer that you put at the end of the BRK heap. So there are reasons why that might work. Like if you're running a guest that does not use BRK for most of its heap allocation but uses mmap, then you're fine. But yeah, that in the general case would not work super well because other threads doing malloc could call break arbitrarily. Anything that we run inside the remote process context needs to be safe against time of check, time of use vulnerabilities, and it needs to be safe against just the normal activity of other threads in the process. So those are some restrictions we have. The current threads stack is actually like intended for exactly this kind of storage, so it's not super weird for the equivalent of a system call to borrow a little bit of stack space to get its job done. But you know, it involves crossing a security boundary, so that's something to keep in mind for sure. You know, you can't trust that the memory you put in the traces stack is going to stay the way you put it. You can't even trust that that memory will stay mapped, right? Like you could be writing to the stack, and at that moment, on another thread, using an munmap call that you didn't trap, the sandboxed process could just unmap that memory. So that's actually the reason why I'm not mapping any of that memory directly into the tracer right now. I'm using read and write on the memory file descriptor to access that memory. Which is a common technique for debuggers, where you want to be able to ask the kernel to read some memory for you, but not crash your own process if that memory is actually unreadable. There are other ways of doing this, like you could catch the crash. You could write a segfault handler that recovers. It could recover to sort of arbitrary degrees, like you could have... you could even like fork off a process or a thread that does the memory test and catches the seg fault and try to isolate that from the rest of the process, but that seems much more stateful than I wanted. Like it seemed like reading from the memory file descriptor was simpler than trying to catch the seg faults when they happen. But we could change approaches later. Like that's easy to change. Yeah, time of check, time of use is hard. Like anything that involves passing strings in and out of system calls gets complicated like this really quickly with the failure modes. I'll be right back. All right, I feel like I've been talking enough. I'm just going to dive into some code, but feel free to keep asking questions and I'll keep trying to pay attention to the chat. All right. I was about to do the thing where I'm already in Emacs and I was about to open Emacs. Which, the very last stream I was using Atom and I kept threatening to switch back to Emacs because I was getting annoyed at Atom, and I did that and I've been pretty happy since discovering Doom Emacs. I might just be weird, but it's kind of cool. I don't know. So what do we got? For anyone who's curious about just like the overall structure of this project, it might be easier to kind of poke around GitHub than watching me like fly around the editor. But kind of the basic pieces we've got here are, there's a Rust library, and then there's this kind of nested project called Sand. I would love to find a better way to do this if anybody who's like a Rust build system expert watches this. Because I have sort of a weird build here. It needs to be a Rust library, and it needs to be a fairly easy to use Rust library, or at least that's my goal. But it also has to build an entire binary as part of its build process, and then include that binary in the library. Not link to it, but include the entire thing. So it's a very weird requirement, and I have not found an extremely clean way to do this. The way I'm currently doing this is that I have two separate cargo workspaces here. There's a main outer workspace. So if you look at this cargo.toml, it'll be kind of normal. I have some dependencies for the command line binary. And then I have this internal crate, which I never actually build from here. I think I was experimenting with that, so I left it in the dependencies list. But this is a little weird, because if I actually try using this, it doesn't really work. It's just kind of in there for semantic reasons. And then there's stuff that I use in the higher level runtime portion of this. So this is like what you would link in with like your Rust network application or whatever, like the video server I'm working on. It's pretty high level asynchronous Rust code that uses stuff like Tokio and Serity and fun libraries like that. But the main big dependency here is probably just like Tokio, and this DK registry library is a thing for Docker registry images, which does most of the work in connecting to the registry and retrieving the configuration JSON and retrieving the actual binary blobs. And then the code that I've written on top of that caches the binary blobs and decodes the configuration and sets up the file system. So this is normal Rust stuff. If you go into source, this is most of the runtime. So this main program is just like a driver binary that I'm using to test this out, and would be sort of basically just a program that acts sort of like Docker, where you can just run an image on its own. But I'm mostly building this as a library that you would embed into other programs. So this is sort of like a command line entry point / test bed for the library, which is mostly just doing this. And this is about how high level I want the API to be. Like, pull a container, wait for the container to pull, give it some arguments, spawn the container, and these error checking things would probably be replaced with a question mark and a better written demo. And then wait here is just waiting for the process to run and finish, and running the event loop in the meantime. But I'm imagining that there would also be a way to attach Tokio streams to files in the file system, or to standard in and standard out, or other file descriptors. And then you could let this run while you have some asynchronous Tokio code talking to those emulated files and doing the input and output around all this. So it would be pretty easy to then make something that's like a network service, where you give it a file, like give it a video file or something, and then it sends it to the container and lets it transcode and then sends it back to the network. Like, that would be a pretty good example for this code once it's a little further along. Oh yeah, and I've been liking Rust. I feel like I've tried to do a couple of projects in Rust now. I think the biggest thing that the first big thing that I did in Rust was the Tuco Flyer project. That one was partially written in Rust. I wrote the server application that handled most of the actual ins and outs of running the robot was written in Rust, which runs on a desktop PC and communicates with the rest of the robot over a network. And then the microcontrollers on the robot, it seems like we could have written that code in Rust, but the Rust microcontroller ecosystem was less mature then than it is now. And there was some really easy to use C++ code that I had handy for that. So I used some C++ code to do the microcontroller side. I'm saying I used C++ code because I was mostly using someone else's network library and then adding a little bit of motor controller code to the network library. But yeah, this has been a nice project, and the video server too, because I've been just digging a little bit more into actual Rust. And then the video server has been more of kind of like this, the high level Tokio IO kind of stuff. And I've also been using async standard for that too. And using libp2p to do IPFS. So that's been much higher level Rust code. And then this runtime is kind of medium level Rust code, where it uses a little bit of async niceness and a little bit of async IO, Tokio, whatever, but it's still somewhat closer to the metal and is still pretty Linux specific in some ways. And as part of this, a lot of this is involved in getting the container ready and setting up an emulated file system. The actual file system is this basically an array of inodes, each of which has some file metadata and possibly a reference to a file that is already mapped in memory. So there's some emulated file system stuff. This IPC server has been the focus of a lot of my work lately. This is actually a Tokio async server that runs in the background while the container is operating, and it communicates with the processes inside the container, specifically with the single tracer process. It communicates with that tracer process via a Unix domain socket, and it passes both messages that are bytes over that socket and messages that are files. And I wrote this weird serializer this week that takes Rust data types and serializes them into these parallel buffers of files and bytes that are both sent through the socket. So I'll show you that in a sec. It's ergonomic, as they would say, but does some weird stuff inside. So the IPC server is one end of that. When you start it up, it creates this Unix file descriptor pair. So we have two sockets, the server socket and the child socket. And this sets a flag, or rather clears a flag on that child socket so that when we fork off a child, we don't actually close that, but we can pass it through into the child process. And then this is actually running the sand binary, which is stored inside the library, so we don't have any like external dependency on that, and it can stay like perfectly matched with the version of the IPC protocol implemented in the library. So the sand binary is effectively part of this library. It just needs to be built in a different environment, and it's included in the library as a binary blob after that point. So we create that and execute it. This internally handles making a command that executes the proper file out of /proc/self/fd. And then I'm adding some parameters that are recognized by the interior process, and the actual file descriptor gets passed through the environment variables. So once the server starts the process, then it makes this asynchronous, or rather we make this asynchronous task right afterwards that waits for messages and it handles the messages. So this IPC buffer is a thing that I wrote like yesterday that handles the serialization of these dual stream messages that have bytes and files in them. And so we can read the bytes and the files. I have not actually implemented the code on this side for sending files from the tracer back to the IPC server, but that is something I'm planning on implementing. There aren't very many cases where that's necessary, because usually the tracer can't open files, so why would it need to send a file back, right? It turns out there are some cases, like if you're trying to use a directory file descriptor to do an open relative to, I don't think it makes sense for the tracer itself to understand the file system enough to do that resolution. I think it makes more sense for simplicity and security to actually send that reference back to the process that's implementing the file system in the first place, and then it can make the comparison and determine, like, you know, is this a file descriptor that refers to a valid directory, and if so, like what inode, and then do the reference. I'm not sure if the process inside the sandbox knows about inodes. It might via like stat and whatever, but it certainly won't be able to like manipulate them in any severe way. Whereas the runtime, like, it owns the entire virtual file system. Oh, that's a good question. Yeah, a couple of good questions actually from Vialine Tev. I'm not sure how that's supposed to be pronounced in Twitch chat. They're asking if I like the async story in Rust so far, and then if I'm using Serity for this, or if I had to write the weird serializer from scratch. Yeah, I'm actually really happy with async in Rust. I mean, I feel like folks need to turn the crank on the libraries a bit more and get them to implement all the right stuff and implement all the right compatibility layers. And I'm looking forward to people kind of migrating more to something like async standard from something like Tokio. But I think it's pretty great. Like, I feel like the way that the compiler gives you all of this power using its type lifetime system and then applies that to an asynchronous system is just really beautiful and amazing, and I wish I had that like 10 years ago. I would have written so many things differently. So I'm really happy with the compiler support for async specifically. And then the library ecosystem stuff for async is certainly not as mature as I'd like it to be, but I think it's pretty good, and I've been enjoying what I've been using so far, and I'm looking forward to it getting better. So yeah, I really like Rust async. In fact, I'm anxious to go through some of this on stream. I got async working in a no standard library environment for this. So the tracer process that I'm using to respond to system calls, it's written in this fairly low level environment where I don't want to rely on any external files, so it doesn't rely on the standard library. I didn't even want to statically link a standard library because I actually wanted pretty careful control over which system calls it relies on. And I can't do that if the standard library is making system calls for me. So I'm using no standard library, no memory allocator, which is kind of an aesthetic decision. I feel like you could certainly write something like this with dynamic memory allocation, but I think it would be pretty great if it didn't need dynamic allocation, and I'm pretty sure I can get that to work. So it's certainly possible I'll give up on that and add an allocator later, but right now I'm really enjoying having everything in there be static, and I feel like that gives me some nice compile time assurances about the memory limits versus the assigned resource limits in the program. And so it's cool. That all works with futures and async. You can just write asynchronous functions, and the compiler just figures out how to turn them into a state machine and figures out how to write a type that encodes all the state that state machine needs. And even though I can't write that type because it's an opaque type the compiler generates, I can use generics to make data structures that hold one of those types, and I can build an async executor around that. It's great. I think that's pretty cool. Yeah, no standard Rust is great. I feel like no standard Rust has improved a lot since last time I looked at it. There are a lot of cool libraries for it. I know I was kind of down on heapless and typenum last time I talked about those on stream, but I've come around. I think it's fine. I think I said typenum was the worst thing I've seen in Rust, because it's this weird library that gives you basically types that represent numbers. It's just kind of a terrible, ugly workaround for a lack of compiler support for having associated types that are numbers. But now that I've looked at how it works in some more detail, I'm less disgusted by it. I feel like they found a relatively elegant solution for something that is useful and doesn't have a better mechanism in the compiler yet. So I'm less disgusted by typenum now. And I'm using heapless for some of this stuff. So yeah, no standard has been nice. And it feels weird using no standard Rust on like an x86 64 machine, because it's like I have a large computer that I'm running all this on, but I'm trying to create like a very tiny environment inside the large computer, and so that's been kind of funny. But I'm excited to try more no standard microcontroller programming too. That seems like it'll be a lot of fun. Oh yeah, so the IPC server, it does actually have a way to send files back, so that does work right now. And I've got kind of this message handler, which I might break up at some point once it gets more complicated. But right now I just have this matcher that's handling a few different messages from inside the sandbox. So I can do things like open process. This is actually one of the more interesting security critical pieces of code, perhaps. I think that the actual interior of that is in process open. But so I mentioned that the main, like one of the main boundaries here is that the code inside the sandbox, which includes the tracer, does not have access to the real file system. It has file descriptors, but it cannot open the file descriptors on its own. So the tracer needs access to memory, and memory is a file. There are ways to get memory access using just the ptrace system call, but I don't think that's effective for the, like that would just involve like way more system call overhead than I'm comfortable with, because you would need a system call for every single word of memory access. And that's just ridiculous, I think. I'd much rather have a way of mapping the memory. To be clear, I don't think it's safe to map the memory into the privileged or into the tracer processes without having a very robust segfault handler that I can rely on. But even the thing I'm doing right now where I have an actual file descriptor, that gives me much better access than using ptrace for two reasons. One is that the file descriptor is reference counted. The process IDs can just disappear at any time, whereas if I have a file descriptor, I have a reference counted handle to that object in the real kernel. So a file descriptor to proc whatever maps actually holds a reference to the kernel's virtual memory structures. So that kind of stuff is super useful. Oh, that's a good question. Question from Twitch chat about what threat model Bandsox is assuming, by the way. Yes. The threat model is interesting. Basically, I want something that can run code. I mean, so there's a pretty wide gap between what I would like this to be capable of eventually and what I actually need for my current needs, which is part of why this feels somewhat realistic of a project. Like the baseline here that we're already doing is running FFmpeg in the same security context as the web app. That's what PeerTube is doing. I don't like it, but it's what they do, and it's what everybody running PeerTube seems to be happy with, or at least they haven't fixed it yet. So that's the baseline. Unless we screw up the security really bad, we're not going to make it worse than that. So sort of at minimum, I want a way to run FFmpeg that is safer than what is currently run, or that is currently common. But the thing that I would like to actually have this be good at is protecting against vulnerabilities in media codecs. So ideally, I would like this to run with semi-trusted binaries and completely untrusted data being parsed by those semi-trusted binaries in an environment which on its own has some privileges that I would like not to expose, but is also still like fairly locked down anyway. So this would be running in a container or something that doesn't necessarily have persistent storage or access to anything important, but this would be an additional layer of security inside that to keep media codec vulnerabilities from getting out of the sandbox. And even just besides the security properties of it, I feel like it is convenient to just be able to run images by hash and give them an emulated file system. So even if this isn't providing like significant additional layers of security, it provides an emulated file system to a container, which is also just useful for getting things to run in the first place. Like you couldn't run things that rely on specific paths without having privileges to do chroot normally. Whereas this is something you can do without kernel privileges to do any kind of file system manipulation because we're not using the real file system. So it feels like there's a lot of room for it to be a robust sandbox, but it's also still useful even if it's just like slightly better than running a normal subprocess. Yeah, the FFmpeg is like my killer app for this. I would like it to be useful in a somewhat broader context, but that's not a giant priority for me. Like I would mostly just like to get it working for simple multi-threaded compute workloads like that. And then the other good question here is about the process VM, read V, and write V system calls. That those are also faster ways of doing ptracing. Yes, I did look at those. I think there was a different reason why I also wanted the file descriptor available, and so it was easy to use read or write. But yes, if the only reason I wanted that file was so that I could do reads and writes, I think I could use ptrace VM rather. I don't remember how allowed those are in Docker. Let's check that. So normal ptrace, you can see it's allowed, but only for recent enough kernels, because I think there was a vulnerability they're trying to mitigate here. Yeah. I don't know how common capsys ptrace is in these environments. Does this have a man page? I forget whether cap sysptrace is like additional ptrace capabilities or just the ability to use ptrace at all. This is interesting too. Let's see what this is. This is somebody. Speaking of this, I don't think I plan on implementing nested ptrace at all. That seems extremely hard to get right and unnecessary for the use cases I care about. So I probably just won't allow that. It's been making debugging kind of interesting, but I think it would be... I don't think implementing nested ptrace would solve that. I think it would just make it even stranger. Yeah, does that mean that cap sysptrace allows you to trace any process? Oh, yes, okay. This is probably in the ptrace man page, actually. That's probably for ptrace attach, whereas I'm using... I think I can work around that because I'm only ptracing child processes in this model. Oh, cap sysptrace. Yeah, okay. Yes, so it's either or. You can trace your own processes. Cap sysptrace is trace anything, which is a very powerful privilege. So yeah, it looks like they chose to just completely disallow reading memory by process ID inside Docker. Unless you have that particular elevation, if I'm reading this right. So I think that's what that means, but somebody correct me if I'm wrong. That's a good question. From YouTube chat, there's a question about whether I'm planning on trying to get Tuco Flyer online in this new place. Yeah, I don't know. I've still got the parts for that carefully boxed up in the garage, and I would like to have a better cat cam solution here. I'm still kind of trying to, like, I feel like I've just barely got most of my studio set up in a way that is mostly sustainable. The couple of streams I did earlier this year was from a like really ad hoc studio setup that I was using to kind of prove out the concept I was going for here, but it was kind of hard to use on an ongoing basis, whereas I've gotten further in that now, but I feel like I need to let Tuco figure out where he likes to hang out in here. And so he and I need to do some back and forth about what cat hangout spots are good, and then I'll make sure that those good cat hangout spots have cameras. And so it might be that there's a way that a moving camera comes back into that. But this place is much smaller. I'm not in the... So like this is old footage in the background here. This is the place I used to live in, out one of the windows at least. It was big and nice, but also super expensive. And so I'm in a place which is much more sustainable now, but doesn't have quite the ceiling height. First Google result is a CVE. That's kind of how I feel about FFmpeg too. Like, I was looking at something recently, just looking at FFmpeg documentation for an unrelated project, and I happened to come across just like the list of FFmpeg CVEs like per year, and there are just so many of them. So that's like a lot of the motivation for something like this. Media codecs are complicated, and they're usually written in C, which is a great way to have vulnerabilities. and they're processing extremely complicated, untrusted data. So it's just an unsafe combination right there.
Can I ask a random question?
Oh yeah, let me turn your mic on.
How does this project compare to Servo Jail?
Servo jail. I forget if I looked into that. Let me pull that up here.
You mentioned jail. I wasn't sure if it was that one or a different one.
Oh, jail. Is that how you pronounce it? Jail? I just now realized that. Thank you.
I think that's the British pronunciation of jail.
Oh, today I learned. That is a good question. Yeah, I looked into this a little bit. This is a sandboxing library that the folks at Mozilla wrote to be a Firefox component. I don't think they're using this in production yet, but it was a pretty interesting experiment in making something that is like a setcomp filter plus namespace filter thing that is easy to use from Rust. So actually, there's a good bit of overlap. The two main differences really, this is designed to be much more of like a low-level component for that you would use inside of another process to take part of that same process and make it lower privilege. So I think the use case they wrote it for was really you're writing a web renderer and you want to have lower privileged web renderers that run inside that, but it doesn't have any infrastructure for like OSI containers, so you'd have to put that on top of this as another layer. You'd have to have something that knows how to assemble containers and assemble file systems and whatever. I looked into trying to use this as a component though, because I mean it is designed to be a building block that is solving some of the same problems that I'm trying to solve. And in fact, it even has some support for non-Linux platforms, which I don't care super much about right now, but would be nice to have. So these profiles roughly map to setcomp filters that it builds. The main issue with this is that, well, I guess the two things, I don't know which one's more important. The one thing is that this does not work inside of Docker in a capacity that is useful to me as far as I can tell, because they do seem to rely on file system namespaces to get file system separation. So I think you could use, let's take a look at this closely. Let's look at what this is actually doing in Linux. So it's got setcomp support and namespace support. Anything using namespaces would not work inside of Docker, but I think it's to some extent optional. Yeah, we're also using chroot here, which we would need to get some help for. Right, like, so the chroot there and these mounts, like, all of that stuff needs some elevated privilege. So the way this works with, normally inside, not inside of Docker, but like on a normal, like Linux kernel, it would create a new process and user and file system namespace. And then inside that namespace, it could be root, because root inside that namespace doesn't mean the same thing as root outside the namespace. But because it's root of its own set of namespaces, it would be allowed to do things like create new mounts and chroot until it drops that fake version of root that it has inside the namespace. So that's how it does all the file system virtualization. If I understand correctly, you can disable that part of this and use it without file system separation, and then you are left with setcomp, which is this side. And this lets you kind of turn on and off entire system calls, but it, like, all this is doing is setcomp, and the thing that I need is basically like a whole thing that's built around setcomp. So this would know enough to build a filter that says like you can't open any files, but this would have no support for like opening an emulated file. it would be nice to use this piece as kind of a building block, but like when I looked at it closer, actually, like this is not actually a library for setcomp. This is actually a setcomp policy. So this is making policy decisions about what should be allowed in this particular kind of sandbox that they're setting up. And so the pieces that I would want to use are actually even lower level than this. They're actually like this setcomp profile library, which I think is using libsetcomp, which is a binary dependency that I don't want to have in this environment. So that's why I wrote this other crate. What did I call this? Yeah, this is basically the piece of that jail project that I can actually use, but I needed to write it in somewhat of a different environment where I'm not relying on an external library to do the setcomp, but I'm making Linux syscalls directly. So yeah, that's kind of why I said I was inspired by this project, but like it isn't directly based on it. I kind of more just like, I like a lot of the pieces here, but I couldn't find any that I could actually use in my project. Oh yeah, somebody else confirms that this is indeed a British jail. I had no idea. Wow. Um, yeah, it's weird that root needs root permissions. It does seem like there should be a way to not require that. I feel like that's part of why file system namespaces exist, was to provide like the low privilege file system manipulation that you want when you're doing something like root. So if you're running outside of Docker in an environment where you have user namespace support, like a normal Ubuntu distribution is configured like this, you can just on a normal Ubuntu distribution create namespaces as an unprivileged user and then be fake root inside of those namespaces and do whatever you want and like do fake roots and whatever. So that totally exists. It's just not something that I necessarily want to rely on as a building block for this project, because then it means that my whole video server is not containerizable. So it's a bit of a roundabout requirement. And I could get around this by just saying, no, you have to run the video server on bare metal, or you have to run the video server on a privileged Docker container. I just don't like those solutions because I want to be able to give people something that is easy to run in a variety of common server environments, which are mostly x86 64 Linux. And it does seem like eventually I could make a version of this for ARM or whatever. It's just, there's so much platform-specific code in this that it's much more tractable if I can focus on a single platform and get that working and then expand it later if I care. And another thing that FFmpeg simplifies is like, I only really want this to run on platforms that are good at video transcoding, which today that's mostly like mainstream x86 CPUs. Or GPUs. That's another thing to talk about later. I would like this to support GPU transcoding eventually, but that might be complicated. I mean, it's probably not that complicated. It probably mostly just involves being able to allow the subprocess to open a real file descriptor to like dev NVIDIA. And it probably involves implementing a bunch of like esoteric CPU garbage that only the NVIDIA libraries use, because that's how this usually goes. But yeah, that seems feasible. Like this architecture doesn't seem like it rules out GPU transcoding. GPU transcoding is kind of difficult for other reasons because, it's not really possible to do the same kind of security isolation there because folks could just find a bug in the GPU drivers or the GPU firmware and exploit that. It's like harder, but it's a much bigger attack surface. So that's the kind of thing where like, maybe if people are doing hardware transcodes regularly on this, they do want to set up like a separate bare metal machine that just does the transcodes and then not use the sandbox at all, but use that instead. Maybe that's what they want to do. But I would like something that's easy to deploy for the kind of common case where people are running like a PeerTube thing on a virtual private server and they don't have direct access to much on it and they just kind of want it to be portable. Yeah, so there's a bunch of other stuff here that is in the same general problem domain. So it took me a while to actually reached the conclusion that I needed to just sit down and write code. And I mean, gvisor is still by far a much more complete and much more mainstream project in this domain, but I'm kind of trying to see if I can do something simple and rusty. So yeah, this is an interesting kind of security boundary here, because the process inside the tracer needs us to open memory on its behalf. But and so like after this point, I mentioned that those file descriptors refer to reference counted resources in the kernel, so they're nice and durable. Process IDs are famously not like that. Unix has always had a race condition in process IDs where there are a bunch of ways to find yourself with a stale process ID. The process has died and no one told you about it, and now your process ID either refers to no process or, worse yet, a different process than what you intended. So it would be very bad, for example, if the sandbox found a way to use this to open some arbitrary process owned by the same user, and then just get memory read-write access to that same process. So in the video server example, this would be like a vulnerability in the codec. What would be the path there? So you'd have to exploit the codec, you'd have to get arbitrary code execution in FFmpeg, and then from FFmpeg, you would then have to get the ability to send arbitrary RPC messages to the runtime. So you'd have to exploit both the video codec and my ptracer process. Once you've exploited both of those layers and gotten code execution in the tracer, then you could send a message with arbitrary process IDs to the IPC server. And if you did that, you could try to race process IDs on the real like outer system, and you could just like guess process IDs for processes that you think might have been at one time registered as tracees, but might now be something that is a juicy target, and you could sort of guess those process IDs and try to open them. It's a real long shot kind of attack because, there are a lot of steps that make even that, like even if you have a vulnerability in those first two layers, so FFmpeg and the tracer, then finding a process ID that represents a good target is very difficult in this environment, because I think all system calls that actually let you directly interact with processes would be blocked by setcomp. But even if all that happens, you could craft a message like this that has a process ID that refers to a process that you maybe used to own but are currently in the process of no longer owning, and different parts of the system may or may not know about this yet. So that's why I have a check where I am checking before and after opening the mappings. It's still possible maybe I'll think about this more and realize there's a vulnerability in this, but I think this is safe. So this is something that happens once per process when it's starting, so when the tracer is initializing or right after a fork, the tracer task that's associated with that process will, and I'm using task in the Rust async task sense. So it's an async task running on the tracer's single thread, which will when that task is starting up, it will do this kind of handshake with the tracer. Like the tracer and the task that's being traced and the runtime all kind of have this sequence that they go through where the new process has to ask ptrace to be traced. If it's a forked process, ptrace will already be tracing it. But the first time this happens, you have to ask ptrace, and then we have to block on a signal so that we actually wait for the tracer to attach. And then there's a message that the tracer task sends to the IPC server to open the process, and we get the reply. So all of that is just like this canned sequence that happens when a new process appears. Right now I only have one process, but this will be the same for sub-processes. And so when that happens, we get this message. This is stateful, so we can only open the process once in the IPC server. And when we do open the process, first we check to see if the process is currently being traced by our single tracer process ID, which is also, like the tracer is much simpler if we don't have to worry about threads internally to the tracer, because stuff like this, like ptrace doesn't itself know about threads. Ptrace is a process-based API. So if we have a single process, which is always in charge of tracing everything within the container, it makes it a little easier to make this check consistently. So this is the main check. If someone exploited those first couple of layers in the sandbox and sent us a bad process open message, then this would be where we find out. We would find that this is a PID that does not actually belong to the tracer. But then if we had that race condition I mentioned, then we might get further. We might open the two mappings and then find out that that process ID no longer belongs to the tracer. There is still a slight race possibility where maybe this PID has disappeared and a different process, which is also being traced by the same process, shows up under the same ID. And we could potentially get those confused in this tiny piece of code here. But I'm pretty sure that the state for the actual tasks, that wouldn't be a state we could actually reach. Or that if we did reach that state, and so like if somebody exploited the tracer and so like if somebody exploited the tracer, we don't care about them additionally making the tracer like get the wrong maps to processes that it already owns. Like that isn't an escalation at that point. And if nobody's exploited the tracer, then the message here always, like if nobody's exploited the tracer, the syspIDs are always valid, first of all. And if somehow we ended up still having an invalid syspID and two different tasks were racing the IPC server over the same syspID here, then like, I still don't think that would matter. I think they would just end up with the wrong file descriptor, but there'd be no security escalation. So this is like the dodgiest bit of security that I'm finding myself having to confront so far, but I think I found a good solution for it, but we'll definitely need a way to test this in detail. So this seems to be a reliable way to take a process ID that the tracer has given us, verify that the tracer does in fact legitimately have a connection to that process by asking the kernel if this process's single tracer is identical to this process. And then we can open these file descriptors. And once we've opened these file descriptors, they will always refer to the same kernel resource because that resource is now reference counted and owned by the file object. And that check can open thing reads proc status. Yeah, it reads proc status and it's looking. I found somebody's Rust library that parses proc status, and I tried using that, but it was failing because it was trying to parse the file completely and like panicking if it came upon anything it didn't know. And like Linux adds new stuff to this pretty often, so it seemed much more reliable to search for an exact regex. So I can find the exact piece of text that indicates that this is the process I'm looking for, and then just search for that piece of text rather than trying to parse the whole file. I guess that isn't exactly what I'm doing. I could actually format that string with the numbers in it and then search for that string. Searching the regex and then parsing the numbers seems about as good, though. Something I might change later. So yeah, this is still the runtime environment. It's the thing that runs inside your kind of cushy application that has all the libraries and all the networking and all the memory. This sand directory is the little tiny thing that runs inside the sandbox. And it is actually pretty small at this point. Being no standard library Rust, it actually does get pretty little. So that's 163 kilobytes right now. Just doesn't seem too bad. You end up with a complete copy of this in memory for every entire sandbox you create. Not for every sandbox process or every sandbox thread, but like every instance of the tracer will have a different copy of this in RAM, which is not ideal. I might find a way to change that later. Maybe I create a single memfd for the sand process and then exec that memfd multiple times. That would require writing my own code instead of using that pentacle library, but that wouldn't be too big a deal. Lots of potential bike sheds that we can dodge for now. So this code is a little more interesting though. This is the code that runs inside this weird little environment. So it's no standard, no main, uses a bunch of features that are not on by default in the compiler. Only compiles with nightly Rust right now. And it actually gets run multiple times. So the first time we run it, this is looking for the particular parameters and environment that we passed in from the runtime. And, so what is it checking? It also checks to make sure that it's executing from a memfd, which I can't think of a security reason why this actually helps, but it seems like it's an easy check to do just to make sure that things are as we expect. So I'm doing that anyway. But mostly it's checking to make sure that we were called with the right parameters. And so we get the fd out of our environment. The reason we still have access to this fd is that this is a child process of the runtime that created the file, and we passed it through inheritance. So this is before we actually have a way of passing file descriptors through a socket, because we don't have a socket yet. This is the socket. The way we actually get the socket is by explicitly marking it as not to be closed on exec, and then execing. So this tracer thing is delicious. It's this is where I got the async code working. So yeah, we'll dig into that a little deeper. I had a hard time figuring out how to actually structure this code without allocating any memory. Because it's pretty common that once you have one of these complex future types that Rust generates on behalf of your asynchronous function, it's this unwieldy object that's sort of unknown in composition. Once you start using it, it has to stay pinned into the same memory location. Like, it's a kind of a weird object, and there are some weirdnesses about dealing with this object in Rust. And it's common to kind of shuffle a lot of that under the rug by putting the future in a box, which is a memory allocation type, and then using the boxed future. So boxed futures are a very common thing in code that is asynchronous and uses memory allocation, but we don't have them in no standard or without a memory allocator. So the idea behind this is that this task function, this is the asynchronous function that is kind of the entry point for every other asynchronous function. It's like the asynchronous per task main. So one task in this context is both an asynchronous task that runs in this Rust thread, and it's one process that we're tracing. Those have a one-to-one relationship. So sometimes you'll see this code talking about processes, and sometimes you'll see talking about tasks. And there are, processes are a kernel object and tasks are a Rust object, but because of that one-to-one relationship, there are some overlaps in how the terms end up being used. So this task function gets passed in here so that it can be captured by one of the type generic parameters on this tracer. So as soon as you invoke this tracer constructor, the Rust compiler takes the complicated opaque type that is actually returned by this task function, plugs it into the generic variable in this tracer object, or in this tracer struct, and now this tracer has a kind of composed type that only the compiler knows, which has all the type information necessary to make the tracer itself and to store all of the per task state that's used by the task function. So, for example, if we allocated a bunch of memory in some async code somewhere, that would end up getting included in the state machine that the compiler generates, and then included in the type that we end up implicitly passing into here through task function. And then it would be allocated on the stack right here. And that's how that actually works. So as it stands right now, this is allocating like several megabytes on the stack. I'd actually kind of rather that we put that on the heap, not a dynamic heap, but just like a static heap allocation. I have not found a way to do that in Rust yet. Maybe I will find one later, or maybe someone who knows more about Rust magic than I do can tell me. But the way I understand is when you make a static variable, which does end up on the static heap, I think static variables have to have types that you can write in their entirety, and you cannot write the type of an async closure, which is what task function is. So if I understand it correctly, this is the best I can do right now without either an allocator or something that I don't know about yet, I guess. So one thing that's a little bit weird is that if this whole object, the task and the task state for every process, so I should mention that part of the reason this is so big is that it exists for every process in our system. And we have a fixed number of maximum processes that we support. I have it set to like 1024 right now. So, and this is kind of the philosophy of static allocation, right? Like you decide ahead of time how many of these resources do I need or do I want to support, and then you let the compiler map those resources exactly once into addresses. That's like the dream. We're almost there, because if this was a heap allocation, not a heap allocation, but a static heap object, the compiler could allocate that heap space statically and give us just like pointers that are known at compile time for everything, which I'm always a fan of. So there would always be a way to know what virtual memory a particular virtual process is using. And you'd never have memory leaks because you're never allocating memory. So this is almost there. Like it's effectively static, but it gets assigned to a stack address at runtime once at program startup, and then everything is relative to that stack address allocation. That means that if this is larger than the stack, you will segfault right away. Which, anytime I put something by mistake into an async function that I didn't mean to put there, like I put like a 4 kilobyte buffer into an async function yesterday, and then it crashed because I exceeded the stack allocation size. And so what that does is this type blows up into something much larger, because now we need a copy of that 4K buffer for every single task potentially. And now that larger object still needs to be allocated in the stack. And if it's larger than the default stack size, which I think is usually like 8 megs, then the Rust stack allocator, which shows up as Rust probe stack in the debugger, because it's checking the memory pages to make sure they're actually live and wired to the allocator, or wired to the virtual memory in that task, it will just segfault right away. So you'll find out really quick if your task is too large. Yeah, so the main function is pretty simple. It's mostly just trying to figure out what we're doing and then doing it. The first time this gets run, this is an event loop that handles everything for the tracer. This is actually the source of a lot of complexity so far. I mean, at least I've been trying, I had an interesting time like figuring out how to actually make this work. Because I needed a way to have my single thread asynchronously process events both for processes and sockets, which is just not a thing that Unix-like operating systems make super easy to do. If I was using somewhat more modern kernel features, there's actually a way to get a file descriptor that refers to a process, which I know it's great. It avoids the race condition, but I can't use it because it's too new. It was added like last year. It's not in anybody's seccom profiles yet. Eventually that'll be a thing, but like for now I just have to ignore that because it's too new. So yeah, without a way to get a file descriptor referring to a process, there's actually a separate system call you use to wait on events from a process called waitID. It's called waitID instead of waitPID because it handles a couple of other kinds of IDs also, I think like task IDs and group IDs. Or task group IDs. I don't know, man. Unix has so many kinds of IDs. But most people use it for process IDs in ptrace. It's kind of one of the to-do list items here is to actually lock down that system call some more. So in seccomp, I explicitly allow all the forms of that I don't completely need myself. Oh, good question. Where Tuco is? I don't know where Tuco is. I had this spot set up for him, and he was hanging out with me earlier. But
he's over here.
Oh, Tuco's over on the other side of the room. Cool. He found a warm spot next to the monitors on my desk, but he's not in a spot where I can easily get him on camera right now. So yeah, we run this event loop that handles process events. So this is anything that ptrace notifies us about. This is all kind of an extension of what used to be a fairly simple part of Unix, where when you make a child process, you can get notified when the child process dies or has some other events happen. And then that just blossoms out into all of this other stuff where, oh, you can get notified when your ptrace process has a system call or when the system call stops or, when a seccomp event happens or, a dozen other things. So when you set up ptrace to do the notification, so like ptrace itself kind of enables the notifications, but then you still have to get the notifications. You still have to do the control flow to wake up your process at the right time. So that's inside the tracer. That's basically what this whole file is about. Yeah. So I mentioned that this was parameterized according to a type. So this is the complicated type that only the compiler knows, which is generated by the async code. And to construct a tracer, the compiler has to already have all the information it needs to figure out the type of the async task itself. So that's why we have to take the async function and then pass it into this constructor. So the constructor has the type already. There might be a cleaner way of doing this, but I couldn't figure it out from playing with Rust for a while, so this is what I ended up with. And then it passes that furthermore into this process table, which is how we have kind of separate state for each process. And then this IPC object is a wrapper around the socket that we use to communicate with the IPC server. And so this is a thing where we can receive and send messages, and the messages are a combination of bytes and files. So then run is really the only thing that main program does. And pin is a weird part of Rust. It took me a while to wrap my head around pin enough to understand how to use it in this project. Pin is a way to manage guarantees about whether or not it's okay to move memory in Rust. So Rust normally lets you move memory at pretty much any time. And moving means you kind of preserve the identity and lifetime of an object, but give it a different physical piece of memory to live in. So if you were to move a string, for example, you might move the actual bytes that refer to, the state of that string, like the pointer in it and the length of it or whatever. It wouldn't necessarily move the string's contents because that's actually a separate piece of memory. But when you return a string, for example, you would move that string object itself from the return value of that function to somewhere else. And so the compiler might optimize away that move, but the Rust language allows that value to change locations. And so pin is a way to manage expectations when that is not actually okay. And that comes into play when you have self-referential objects. So if you have an object that makes a reference to itself, now if you move that object, you've broken the reference. And I'm starting to get into the area of this where I don't really understand it well enough to talk about it in much more detail. But like basically when you make a pin around another object, you're making a guarantee that when the object, I keep using object because I'm used to object-oriented languages. Rust doesn't actually have objects. The word object doesn't mean anything in Rust. I think what I actually mean here is value. So when you pin a value, you get an instance of this pin type here. And so pin itself is a type. I think specifically it's a struct, but I'm not sure that really matters in this case. And when you call this pin new unchecked, the reason this is unsafe is something I'll get to in a sec, but you can often create a pin on just some random value, and then you'll get a value that that has this guarantee wrapped around it that the pin says this will never move. So there's a trait called unpin, which is implemented by default for most objects, which says that even though you've asked for this pinning guarantee, for this particular object, that guarantee actually doesn't matter. It's a way that the compiler and or object implementers or type implementers can signal that okay, like this has no self-references, it's okay to move it, whatever. So most types are unpin, and if you were trying to pin something fairly normal, like if you had a boxed future, for example, a boxed future, I think is pin because, or is unpin because the box itself is fine to move. The actual future itself can be pinned separately. But the problem here is like async functions, these complicated types that get built from async functions, that's actually like the use case where pins need to not move. Like when you have a local variable in your async function that references something else, that's going to have a whole bunch of self-referencing data. So the async closures are very canonically not unpin. So like once you pin an async closure, you have to be prepared to make a strict guarantee that that object will not move. So there are a couple of places where like Rust cannot reason about that itself, and I have to be responsible for that and use unsafe code. So I think right here, yeah. So what I've done here is in process table, I'm assembling a bunch of those futures using task functions. Like I'm assembling a bunch of those types into an array. And then once I've done that assembly in new, I can take that entire array and wrap it in a pin, making that guarantee that it will no longer move. And then once that whole thing is pinned, I can go in and access individual parts of it in a way where those individual parts can be pinned or unpinned depending on the type, the specific type needs of that part. And that's called pin projection, and that's what I'm doing up here. So the entire tracer can be pinned. When the entire tracer is pinned, I'm saying that the process table is also pinned. So when I pin the entire tracer here, I can go in and get a pinned process table, and then by extension, I can go into the process table and get a pinned future for that single task. But the socket doesn't care about pinning because nothing in there is self-referential, so I'm saying here that you can get just like a regular unpinned reference to the IPC out of the pinned tracer. And this is all handled by a crate called pinproject, which is not part of the language, but is kind of a nice little add-on there. So the actual event loop, once I've set this all up, so spawn here is calling ourself with the other mode. So fork is actually, like this is actually the real Unix fork system call. And this returns different values depending on which process you're in after it returns. Like when you call fork, you are now two processes instead of one. And one of you is on this path and the other of you is on this path. So this path is going to be the child process. which sets it up to be ptraced, and then calls exec. And then the other is the kind of non-child process, the like parent process, which has the same process ID we started out with. And that gets returned a copy of the child's process ID, and we can set up its state to start running a new task. And the actual event loop just kind of simultaneously tries to receive messages over ptrace and over this IPC channel. The reason this works at all is that we are using asynchronous I/O signals, which is another somewhat esoteric part of Unix that I'm using. So when you're doing asynchronous I/O, there's a bunch of ways to make it happen. Like if you're using a high-level language like like JavaScript or something, like Node.js. One of the reasons Node.js got so popular is that they made a really nice JavaScript wrapper for a fairly high-performance asynchronous I/O implementation, and just made that easy to use and popular. And so what that's doing under the hood, like when you do some async thing in Node.js, when you do some like async file read or whatever, at the very, very core of that, you have a single system call, which is asking the kernel, hey, I've got this representation of some things that might need to wake me up. Why don't you put me to sleep until one of those things happen? The kind of most powerful form of this on Linux is epoll, which is a way of making a kernel object that you can kind of dynamically add and remove wait sources to. So epoll is cool. The classic way to do this is select, which is the like old school Unix version of that, where you're always copying arrays of file descriptors, but it does the same fundamental job. But there's some more esoteric ways of doing that. So async I/O, the way that works is you set parameters on a file descriptor to say, when you're ready to read, please send a signal to this process for me. So it's a little weird, like, right? You're setting a parameter on a file descriptor, which then causes the kernel to send signals on your behalf. So like that kind of thing specifically is the sort of thing that I will have to be very careful to firewall off in my seccomp profile. There's a to-do note about that right now in my seccomp profile. Right, like right now I'm allowing all of F control in the tracer, but I don't actually want that. Like I want to lock that down so that you can't, for example, deal with signals, because I don't want process IDs to be exposed inside the tracee. Yeah, there are actually slightly different profiles here for the tracer itself and for processes the tracer is responsible for. And I might make that even more fine-grained, since I think I can probably drop exec permission from the tracer as soon as I spawn the process. So like I've got some notes about I need to make this policy more strict, but right now it's just kind of like a work in progress. It's already way more strict than Docker though. Like, and it's my intention to keep it very minimal. All right, let's go to the other editor. I'm getting tired of the web browser. Let's see. Yeah, I think maybe the next stop is the IPC file. Why do we have Clippy warnings here? I am pretty sure this is one that Clippy is getting wrong, but let's try that. I was pretty sure this is a trait import that I actually need, but let's see if it compiles without that. Yeah, I haven't gone through and cleaned up all my Clippy warnings yet because there's a bunch of dead code which is intentionally like a work in progress. Oh, I guess that does compile. Thanks, Clippy. I'm sorry I doubted you. I thought I needed that trait, but Clippy is very handy. I'm glad I set up a so I set up Doom Emacs kind of recently, which is just a package of just like a kitchen sink package of add-ons for Emacs. And it does actually have some really nice stuff for Rust. Like it integrates with the Rust language server and gives you like real-time information about warnings and errors in most cases. And it's pretty nice. So yeah, this IPC socket thing, when we start it up, we do this setup sig.io thing. And this is all a little bit weird at the moment because I don't know, like Rust in general tries to discourage you from doing global state and generally makes it easy to have things not be global and hard for things to be global. Signals are extremely global though. They are very per process, like well, per thread in Linux really. Linux threads and Linux processes are really the same thing. So I need to be getting this just like single global notification, but it also pertains to a specific file descriptor. And if I was writing a more complicated application here that was actually going to be waiting on events from multiple file descriptors, there are some features I could use to have sig.io tell me which file descriptor it is, but I don't see it getting to that point. I feel like having exactly one file descriptor is a good place for the design of this process, or at least exactly one file descriptor we're waiting on. So we have this like really simple sig.io thing here that just sets up like a single sig.io handler and uses a global atomic boolean to keep track of whether the signal has been invoked. So this is actually a real signal handler here. Where's signal? I think some of the signal utility code is in my nolibc module. Yeah. This is something I might pull out into a separate crate at some point. I've been writing this just like a little library of stuff that I've needed that is specific to not having a standard C library. So it's got like, this is where I define print. So if you needed to write your own print line, sometimes it happens. So I've got a print macro and a print line macro because I'm not using the standard IO library. And if I was using the standard IO library, it would be doing a bunch of stuff that I don't want. So I needed something a little lower level. What? Tuco is... I don't know why anybody cares about Tuco's gender, but Tuco is actually a male cat. It's like weird that cats have gender. So yeah, I had to write a panic handler. So like basically everything except startup.s. For some reason, the actual assembly language startup routine that gets you from your process just got control to the first thing that you can write in Rust is actually still exists. It'd be cool if you could go even lower level than that. I don't know if there's a way to do that in no standard. So yeah, when you're in no standard mode in Rust, at least on Linux, it does not link with libc, but it does link with something that's equivalent to like libgcc, like the compiler's internal standard library. Or at least it sort of does. I think this is maybe part of no standard that's a little bit weird right now. Like there are parts of it that will try to link to like memcopy and memset, even though those have not been defined anywhere. So that's why there's this crate called compiler built-ins that provides that. So that compiler built-ins crate is clearly trying to take on the role of something like a libgcc, but this is still using a startup.s, which seems like it was right out of libgcc and is making the assumption that functions like this are here. So that's why I have like an unreachable main, unreachable libc, csu init, like whatever. Like these are functions that startup.s is calling, that are not even calling, but taking the address of, that I don't actually want. So this is like the interface between libc and the startup code. The startup code normally calls this thing libc start main and gives it a pointer to these functions. And then it invokes the C main. I just didn't want to bother with that, and I put my main code right here. Startup.s is still giving me like a C-like argc and argv. If startup.s did not exist, we would have to pick these out off the stack ourselves with some somewhat lower level code. So that's kind of handy. But then these are just C pointers, so this does have to use some unsafe code to access them in Rust. And then actually calls our like slightly friendlier main function here. And then the signal handlers are also kind of bizarrely low level. Like, this is one of those things where like none of this is really documented. You have to read the source code for Linux or libc to figure out like really specifically how this works. So if you read the man page, it seems like you should be able to call. Okay, so first of all, the man page doesn't really talk about the system call. The man pages describe your C standard library API for the most part. So if I do man signal, this talks about how you would normally do this from a program that uses the C standard library. You would call signal, you give it a signal number, you give it a sig handler, that'd be fine. The thing that we're actually doing is a little bit lower level than this, though. We're not calling signal, we're calling sig action, which is kind of more general purpose. And there is a libc wrapper for that. So if you looked at this, it actually uses the same. It is a structure that is named very similarly to the one the kernel uses. I might be getting this slightly wrong because it was like a little while ago that I actually wrote this section of the code, but I think there are actually 3 separate versions of sig action for the kernel, the libc, or sorry, the kernel internals, the kernel ABI, which is used by libc, and then the libc ABI. So if you're like an application using libc, the version of sig action that you see here, if I'm remembering correctly, is slightly different than what the kernel is actually using, because the libc wrapper kind of does its own thing. Yeah, sig action is defined as something like this, but the actual definition is a little bit weirder. And this restorer. So the man pages are just like, restorer is super platform specific, don't touch it, leave it alone, leave standard library alone, it knows what it's doing. But it turns out that is actually necessary from the kernel's point of view. It's not just a standard library thing. So even if it seems from the man pages like restorer is optional, and you could have the signal handler defined, and then the signal handler could just invoke sig return on its own, that seems like it should work from reading the man pages, but the way Linux is actually coded, it will just throw away your system call immediately if you don't set SA restorer on Linux. At least on Linux x86-64, because this is definitely architecture specific. I don't know about x86 32-bit. It's been nice to ignore 32-bit for this project. Gosh, I remember I have some bad memories from having to write platform code that supported 32-bit and 64-bit simultaneously. But yeah, we can just ignore 32-bit for this project. But yeah, if SA restorer is not set, the kernel will be very angry and will just error out your syscall. So you've got to set SA restorer and SA flags up here. And you actually have to provide a restorer. And the restorer, it gets... So how does this actually work? So signals. Like signals, I mean, I don't know how familiar folks are with signals already, but like it's a Unix feature that used to be something that I think application developers were much more in touch with. It used to be much more common that when you're writing a Unix program, like, oh, you want something to happen, like you want to get notified when somebody presses Control C, like, oh, you can set a signal handler and get notified. And like that's still how you do things in C, but like signal handlers are notoriously hard to get right because they can run basically at any time, including inside the standard library. So there's a small list of functions that it's actually safe to call inside of a signal handler if you're using the standard C library. And it's much more common for people to try to avoid doing work in the signal handlers and just like set a flag or put something in a buffer and then do the actual work later. So it's kind of hard to use them effectively. And in more modern programs, it's common for signal handlers to not really do much work, but just to kind of set a flag and let the main program do some work. Um, but the way they actually work, I mean, you might, if you're familiar with embedded programming, these might sounding like interrupt handlers. And the way they're implemented is they're basically user space interrupt handlers. So in a normal CPU interrupt, the CPU at any time will take your running code and effectively stop it and call something else. And the way it does that is by, in hardware, generating usually a stack frame that has the return information to get you back to the original spot. And this is all incredibly architecture specific. Like some processors don't do this, and you have to have some special code in your signal handler to figure out or your interrupt handler to figure out where the interrupt came from. But it's common on like modern processors like ARM and x86 at least for interrupt handlers to mostly look like function calls, sort of, with some caveats. So signals are a lot like that. They mostly look like a function call, but they have this weird context where they can just happen at any time. And the way the kernel actually implements this is much like how hardware does interrupts, where it isn't just at any time. I think the kernel only does this when you're returning from a system call. So I might be wrong about this, but I think that it's the case that a process can't receive a signal if it's just in a tight loop, just being CPU bound and not doing anything. You can still kill that process by sending it a sig kill, because sig kills don't actually have to be delivered, they just kill the process. But I believe a process can't actually receive a signal unless it's returning from a system call, because that's how they're actually sent. So on return from a system call, normally the kernel would just put the CPU state back, let the process continue, but you can modify the CPU state before you put it back. And so you can modify the CPU state by putting some stuff on the stack or changing the instruction pointer or doing all of the above. So you can return from the system call to a different location than where the system call was invoked. And fundamentally, that's how you make a signal. And so sig return and sig action are involved in getting back out of the signal. I think the reason this is architecture specific is that on some architectures this was not necessary, and they found a way to make the signals return just like a normal function. But I don't know the details of why this was necessary on x86-64, or even if it is still necessary, or if it's just like a vestigial thing. But the way this works on x86-64 at least, is that the kernel builds a stack frame such that it will, when your signal handler returns, it'll return into that SA restorer, which should be a pointer to some code. It's important that the SA restorer is not a full-on function with its own stack frame, though, because RT sig return will just completely it'll completely just end this function, right, and pop a frame off the stack. So if this was a function call that would have any kind of local stack state, so if this was not a naked function, if this was a normal Rust function, then its prolog would pop, or would like push a stack frame pointer at least, and that stack frame pointer would misalign the data that sigreturn expects to see on the stack, and this would just crash. So it's a very weird architecture-specific thing, and I don't know where code like that lives except in a library like this. I'm glad some folks aren't bored by the Rust streams. I feel like I've it's like hard to say I actually enjoy any computering anymore, because I feel like there are a lot of really good reasons not to enjoy computering, but to the extent that it is possible to enjoy computering, Rust seems pretty nice. Like, I actually really like the language and the community, which seems like a miracle as far as computering goes. I also just feel like the language itself just, I don't know, like it really speaks to something that I find fundamental about programming. Like it's not trying to make a new thing that is sort of arbitrarily simple and easy. It is trying to make a really faithful representation of the specific level of complexity that computers have. And I find that compelling. Like, it's not trying to kind of smooth over everything about memory management. It's trying to give you a system that lets you manage memory in the same detail that I would want to manage it manually if I was writing C. But now the compiler is making sure that my code is much safer than it would be if I was writing C. So I think it's pretty cool. So yeah, big old event loop. That task function is actually where things start to get kind of interesting. So a lot of that stuff is in this process subdirectory. I'm having feelings about this process directory. I don't know if it needs to be renamed or made into not a subdirectory or something, but basically a lot of everything that involves per process or per task state is in here pretty much. I started out this directory when I was writing the process table, but then it kind of ended up taking the task function as well. So the task function itself lives in this task file, and process task. And there it is. It's just one line. So simple. Yeah, I mean, we wanted to construct this object inside the task function so that we didn't have to pass it into the task function. Could we pass that into the task function? I feel like there was a reason related to lifetimes where this made more sense, but this might be something I could change. This might be cleaner if I construct the object outside, and then task function is actually just... No, I think this... So I need the type of this task function to be pretty simple, at least as simple as I can make it. So I think it was nice to keep this task structure itself out of that type. I could go back and forth on that. See, but we've got these great data structures like a stopped task. I find stopped tasks great. It's like when you have a task and it's stopped, you can make one of these data structures and you get a mutable reference to the task, a mutable reference to the user space registers, and it's great. And you can't like hold on to a reference to a user space register while the task is running, because for the task to run, we have to be able to stop having a stopped task. So I love using Rust's type system to maintain invariance. So yeah, a lot of the task is implemented in... Oh. No, there was a great reason for this. Okay, I'm remembering my own design decisions belatedly. That's right, task new is async, and everything async has to go in this function. I did start out actually with a synchronous task new, but then I decided that I wanted the task itself to only be constructible once we have a process handle. The process handle is something... So that is actually a reference to the memory in the process. It's like one of those powerful operating system objects we have, and we can't get that until we can actually talk to the IPC server and do that process open. So that's where process open comes in. That's the task constructor. So when this task function actually runs, so just to bring this back down to earth as far as how Rust futures work. So this is an async function, which I keep interchangeably calling these async functions and async closures because I think the implementation is the same, but correct me if I'm wrong about that. I think that the way Rust represents the result of this is like a specific future type, which is like an opaque async closure. But like the whole point of this is that you can't write that type. It's opaque. Like the compiler just says an opaque type is here without telling you any information about the type. I mean, the information you do have is that it's a future. Like that is the interface that you get. So this returns a future. I mean, the return type here is the unit type. It's left off, so it returns nothing basically. But because it's an async function, the real return type is actually a future where the output type is the return value of this function. When you actually call this function, because it's async, none of this code runs. This function in Rust acts like a constructor for a state machine. And that's true of all async functions, even higher level code than this. Like when you call an async function, that async function is actually constructing a state machine. So likewise, calling this new constructs a state machine, and then calling await incorporates that state machine into the state machine that this function is constructing. So that when this state machine finishes and returns a result, it unblocks the state machine that this function constructs. So that's how this chains all the way down. Like this function fundamentally is just constructing a state machine which keeps the state of one process/task. But because of all this nice async chaining that the compiler does, we can just kind of arbitrarily use fairly freeform async code here, and the compiler will give us a single static data type that represents the state of all the tasks, and we can just put that whole thing on the stack. I find that pretty compelling. So the new can be async. So some of this is like, this ptrace stuff happens synchronously. This doesn't need to be async. But now we're doing a message. We're sending, I actually have a macro that makes these messages a little bit easier to write, but this one can't use the macro because we don't actually have a task yet. So once I have a task, you'll see this like IPC macro show up later. But because we don't have a task, this is doing it the kind of lower level way. So it's sending an open process message using the syspid. This is the actual system process ID of the new task as we were told by whoever instantiated this task. So that'll be that constructor up here we were looking at before. Not this, but in the main, I guess. Oh, right, this is not where the task function is called, right? Because this is setting up the tracer, but the task function is called per task. So that is actually called a little bit later when we instantiate a process. So that'll be from run. Yeah, that happens in spawn here. So spawn is where we fork off the subprocess, and expect new child is what actually creates the task. So after we get the process ID of the child, and now expect new child is actually inserting it into the process table. And inserting it into the process table is what actually initializes the process, which actually creates the future representing the, I mean, not creates, but I guess creates. It doesn't allocate memory, but it does create a value. I find that a really nice part of Rust too. Like, there are some languages where anytime you make a new thing, that is one-to-one corresponding with allocating memory. But I like how Rust, you can think about values conceptually as things that have, there's a lot of like meaning to their lifetime that doesn't have to be expressed in the way the memory actually moves around on the CPU. That's right, process table. I think I was writing some of this on the last stream. I used to have two maps here, so you could map both directions, and then I realized that nobody outside of the task actually ever needs to map a vpid back to a syspid. So that was unused code for ages, and I just ended up deleting it recently. But yeah, insert. So yeah, we're allocating a process ID. This task data is just kind of a wrapper for all the stuff that we pass into the task function. So it's like your parent process and the current virtual and real process IDs. Because this is the tracer process itself, it knows about both the virtual and the real process IDs. It's really the only place where that's true. Outside the tracer, like in the runtime, the runtime knows about real process IDs because it's running on the real system and all that. But like, I guess really the only time it cares about both is during process open. For the most part, it's communicating with a single task. The IPC channel is basically per task. But this layer pretty much always has to maintain both information about the real process ID and the virtual process ID so that it can do the mapping on behalf of the traced process. But then, of course, the traced process never gets to see the real process IDs. It'll only know about the virtual ones. So process... Oh yeah, so a lot of the stuff in this process table was really weird Rust code because I have to deal with all this pin projection. So yeah, I feel like I still only have like an 80% grasp of pinning in Rust. And so I still might need to revisit how some of this works, but it seems pretty solid as far as I can tell. So this has to be able to take that pinned data structure, and part of what's weird about this is that I have a pinned object here that I do actually want to replace. So I'm not moving it, but I am dropping one and putting another one in. So I think it is totally legal to do. I mean, I think it is not memory unsafe, but it requires some unsafe Rust code to actually make that happen. So like, insert. This is from that pin projection package or projection crate. Yeah, so this is unsafe because right here we're replacing that pinned process object with another pinned process object, and replace actually does move memory. So this would not, if the compiler was just like following the pins and figuring out what's safe, it would say this is no good. But I know that this is actually safe because the process I'm replacing is always none, which means I have to be sure that I'm never inserting a process and like overwriting an existing process, because that would actually be legitimately unsafe. Because the minute, in a single threaded application, I can't think of a way that would actually crash. But if it was ever possible to continue executing that task after replacing it, then I would have a whole bunch of dangling references due to all the local state from that task. So I think that this is safe both because it's a single-threaded program and because I am ensuring that I'm only replacing a task that is none in the array. And I haven't written the code for ending tasks yet, but I think that'll be kind of analogous, where there'll be some interlock where I can only remove the task. I can only set it to none here at the end or at the completion of the future. So right now the task future that I have never completes. But I guess one way I could do this is once the process behind the task actually dies, I can let the task return normally, and then once the task returns normally, the future will be done polling, and I can replace it with a none. And that seems pretty legit. Yeah, this free function is not called yet. This is probably not how I'm actually going to do this, actually. I should just delete this, because it's not called yet, and it's probably not how I'm going to do it. Yeah, I don't think there'll be a way to free a process. I think the process will have to free itself. So yeah, the process table manages the processes, and then the process itself is mostly a container for a task, and the task is like the thing that I don't have an easy ability to like write the type of, because it depends on this future. Yeah, this part seemed like a key realization for how to make this work. making an enum that uses pin project to be pinnable in only one of its variants seemed like a key for this. So there's an initial state that the task has where I want to construct the task, but it isn't actually constructed yet. I have parameters for the task, and I have the type information for the function, but it isn't actually created. And then it can be pollable, or I actually have a future, and the future is actually pinned, or it can be none. So, like, I don't know how much of this the Rust compiler actually knows about, but like conceptually, it would be safe to treat this as unpinned when it's in the initial state or the none state, but not the pollable state. So when the future ends, I could have some potentially unsafe code that sets this state back to none, and then everything after that seems like it would be pretty straightforward. Yeah, this is a lot of the stuff that I needed to figure out in order to figure out how to do async functions in no standard the way I wanted. Right. So the process itself implements a future. Is that what I'm doing here? No, it just has a type parameter that is a future. Right. I experimented with making the process itself a future, but I think I gave up on that for some reason. I might revisit that because it seems like the process could totally implement future itself. But instead it just provides this poll function which has the same interface as a future. So it takes a pinned version of self and then does the things. Yeah, so we're actually looking at messages from two different sources here, right? Oh, no, this isn't about that. This is, sorry. We have all these message queues and stuff. The message queues are how we pass data in and out of the task. Those are using these heapless single producer, single consumer queues, which are basically ring buffers with atomic guards. So these have a statically allocated size. They're circular. You can read one end and write the other end. They're pretty small too. The event queue has 2 entries. The outbox queue has 4 entries. So like, these are just used for communicating values between the asynchronous and the synchronous code. And because this is the interface between the synchronous and the asynchronous code, I think this is where we have like a synchronous message sender and an asynchronous message consumer. Is that here? Here's the synchronous sender. We always expect that there's space in the outbox. What that actually means is that you can't just like send an unbounded number of messages to a task while it's stopped. The way the executor actually works is that you enqueue a message and then run the task. So this never really has to hold much. So yeah, we can send an event to a task, which just synchronously enqueues it in the outbox. We can synchronously check the outbox. These are the like synchronous external API for the process. But then event source and message sender give you these. And the reason all this is unsafe code is that I couldn't find a way using the safe API to, or no, actually, I think this was even in the examples like this. So the single producer, single consumer queue, I don't think that there's a way that they can, just using the type system, verify that you're not using the producer more than once and using the consumer more than once, for example. So the code to actually split this queue and I mean, the reason this is actually unsafe is because of the pin here, but I think it probably would have had to be unsafe for some other reason. Anyway. Way into the weeds there. Yeah, anyway, the split code is weird. There might be ways to improve this. The event source and message sender are these objects that we create that refer to only one half of each of these queues. I think the other reason, so besides the pin projection here, the get unchecked mute here, this is the guarantee that we're making here. So the queue itself has to be pinned. This is not because of the usual reasons Rust requires futures to be pinned, but it's actually because I'm legitimately making internal references here. Like, I'm taking references to items that are in the queue and keeping them kind of long-term in my asynchronous code. So because of that, as soon as I start up asynchronous code, I do actually need the queues to be pinned. So they're pinned as part of the group of stuff that's pinned up here. Actually, everything in process is pinned because all of this has to be referenced by the async code. So event queue and outbox queue can't move after they get pinned. But what I am doing here is, like, this get unchecked mute gives you a mutable reference to a pinned object. And you could use that mutable reference to move that pinned object out. You could also use it to do other things that I don't want with regard to the queue splitting. But I'm guaranteeing, I'm promising here to not move the queue and to only use it in a way that doesn't violate its single producer, single consumer guarantees. But once I've done this bit of unsafe code, I have this single reference to an event source that I can use pretty normally, and now Rust will guarantee that I don't mess things up from there on. So same with the sender. And then these objects, I think, have async. Okay, message sender is synchronous. Oh, right, and this is asynchronous, but I had to write the future type here. So this acts like an async function. Yeah, I don't know why I was thinking send was async, because we don't actually have a way of waiting on send space. We just have to design the protocol to never block on send. So blocking on send is always an error. Blocking on receive is completely normal. And that's implemented using this future. So this is like what actually blocks when we have the async code. So it's like this long chain of asynchronous function calls that the compiler assembles for us, with at one end of the chain, at like the very top of the chain, is that task function that we call, and then a bunch of stuff happens. And then at the very bottom of the chain is this future, which gets waited on somewhere when we make an IPC call or whatever, when we're waiting on a message to come in. And this implements a poll function, just like every future, which checks to see whether there's data. If there's data, it returns it. If not, it says pending. And all of the state machines between here and there propagate that poll pending back up, and now our call to the poll function on that outer future resolves and says pending. And that ends up back in this poll loop. So yeah, that's actually all in the same file. The top and bottom of the stack are both in this process mod. So this poll pending goes all the way through the rest of the state machine and winds up in this poll, right? That's right, I was confusing myself about what this is. This is just the state machine to manage processes that are either not yet constructed or don't exist. So if you try to poll a process that doesn't actually exist, but it's just unused memory, we get a runtime error. But if you poll a process that we're in the process of setting up, then I think there was a reason related to the memory references why I had to do it this way. Because you can't just like take a mutable reference to this. You have to kind of carefully replace it. And then this is actually calling the task function. So this kind of encodes the initial state of all of that. I probably could put these in the task data. I think the reasons these are not in the task data is just that the task data gets passed around a bunch before I actually have references to the event source and message sender. So I think task data is more like parameters that start a task, whereas once you have the event source and message sender, you're pretty much already a task, and task function is just going to call the task constructor with those values. Yeah, and then this unsafe is, again, using get unchecked mute to say, like, no, really, it's okay to modify this pin because we're not actually going to move any of the values. And we're using that to modify the pin. So that's like the secret sauce that makes the asynchronous part of this work. And I was just thrilled when I realized that this was even possible in Rust. And then the actual task code gets to be somewhat higher level. So we have async, and we were just here doing the open. But then once we're in run, this is mostly an event loop, right? Like we're mostly waiting on events from ptrace, which are mostly system call emulations. So, and in fact, there are other things that we will need to handle. Like there are a whole world of signals that the tracee can legitimately get and that we will need to pass on to the tracee or like decide not to handle or whatever. And I've mostly punted on that for the moment. And right now I'm really just focusing on these setcomp traps, which are used for the system call emulation. So that gets to go down here to handle setcomp trap. And then just to keep the task itself from getting too complicated, the actual system call emulation happens in the system call emulator. And that this is the moment where we stop the task, right? We construct the stopped task. It takes it gets this mutable reference to self, which is the task, and we grab a copy of the registers by making a ptrace call, and then the stopped task gets a mutable reference to the register so that it can modify the process state however it wants. We run the system call emulator on it, and then this is just about returning to the underlying process without allowing the original system call to run. So Linux has, I added some constants to make this a little easier to understand. But this is actually just setting AX to -1 in the registers, or the saved AX. It's a way that Linux uses to signal that the system call should be skipped instead of actually implemented if you set the saved system call number to -1. So we're blocking the system call, returning the registers, and then actually unblocking the ptrace process. And all this happens asynchronously, so if the system call emulator needs to like open a file, it can send an IPC to the runtime, wait for all that to happen, and then this can return, and all the while the process is stopped. We have a stopped task representing its state, and we just invoke ptrace to continue once we're ready to continue. So I think this is kind of nice. Like, it would be fun to make a somewhat higher level Rust ptrace library that is also async like this. I did briefly use someone else's ptrace wrapper to play around with some of this, and that was kind of nice, but I feel like I've kind of hit upon an API that I like a little better, so it might be worth trying to turn this into a separate crate at some point. I don't think anybody has a no standard library ptrace emulator that is also async. Anyway, so then the next step here is syscall emulator, which is in the syscall module. So that gets a stopped task, and this is also something I kind of like, is we can have a single point where we read the registers and figure out how to convert them into parameters for the system call. There's like a potential place for bugs to creep into code like this that I've seen in the past, where let's say you're writing a system call emulator and you decide that the canonical representation of the system call parameters is in the register state, and you just have accessors for the registers. It's not too hard to get into situations where if you're emulating a system call that modifies the register state, you can kind of get confused about whether you're in the part of the program that still has the original register state or whether you've changed them and whether you can still access the parameters. So I think it's much nicer to capture all the parameters once canonically and immutably, and then we have this immutable syscall info that we then use to construct the emulator. So, and this is again just like a nice example of how you can use the type system in Rust to make it harder to shoot yourself in the foot. Like any function that operates on a syscall emulator, which is like basically the whole system call emulator, can't do its job unless there already is an immutable reference to this syscall info. So it's a nice way of maintaining that. So this is a big question mark still, because like this next piece of code here, returning a okay, maybe I shouldn't get into that yet, but I need to pass the system calls across remote controlled. I need to pass file descriptors across remote control system calls, and that's what gets implemented here later. So yeah, these, I probably should put the dispatcher first because that's the main entry point. I put the return functions first because I was weird like that. The dispatcher is really the entry point here. Gosh, this is another piece of Rust that just makes me happy. So I've got all these arguments, which I often want to access as a specific type. So if I'm writing a system call like open, for example, it's got a string argument 0, it's got an int argument 1, it's got an int argument 2. I don't want to have to write a whole bunch of like casts over and over again, but it's pretty easy in Rust to just define a local closure here, and you can just pass it the argument index, and because these are closures, they can capture a reference to args, and like, this is absolutely mundane in a dynamic language like JavaScript. Like this would be just like, okay, of course you can do that. It's like whatever, you just reference count everything. But none of this involves memory allocation or compile time, or runtime reference counting. Like this is all reference checked at compile time. So we know that at compile time, nobody is using these closures outside of this scope. And it all gets optimized into basically the same code that you'd get if you were putting this at the call site. So it's just zero cost abstractions is the tagline there. Being able to add abstractions to your code without having to worry about ridiculous runtime penalties all over the place. And in fact, being able to add abstractions without any runtime penalty. It's quite nice. So yeah, this is actually where the list of emulated system calls lives. Right now it's very small because I'm just starting this. I've got some bits and pieces of open. This is not really complete. Like open at doesn't handle directory file descriptors yet. This open is probably pretty much how it's going to look. So it does an IPC call. This is a macro that just kind of automates the process of sending a message, then waiting for a response and checking that the response has a specific type, and throwing a fatal error if the response had the wrong type. In fact, none of this is opaque. We can just look at the macro. Where does this macro live? I think it's here. Yeah, way at the top. So yeah, this needs an actual task, so we can't use this outside of a task. Which means this only runs on the asynchronous side of it all anyway. So then we're synchronously sending the message, which is pretty straightforward. And then receiving the message is what actually takes enough code that it was worth putting this into a macro. And this just uses a match to look for a specific type of message and decode, or the way you'd usually use this is put a pattern that represents just a single message here, and then this would be the arguments that are captured from that pattern. Oh yeah. So yeah, we have our task, which is inside the stopped task. And then in the case of open, that maps pretty much directly to one of these IPC messages. So, the process in the sandbox wants to open a file. There's not much to do with that other than pass it to our file system implementation, which is on the other end of the IPC channel. So we're passing out this message. So from sand file open is a enum variant that specifies the operation we want. And then we've got this file access, which is really just the shared components of system calls like open and access, which are about getting access to a file. It's the optional directory that you're doing the lookup inside of, which I haven't implemented yet, but I reserved some space for that. And then the path is a pointer. So this is actually a memory address in the tracee. It's not trivial to read that, and also, if we're going to read it, we have to only read it once. Otherwise, we have time of use vulnerabilities. So in this case, one way to implement this might be to read the string in the tracer and then send the string over the inter-process communication channel. But I decided that a lot of the architecture for this seemed to make more sense if the inter-process communication channel was really not about sending variable length data. I should visit the IPC next, but I thought that the IPC layer made a lot more sense if it was about sending just what Rust would consider values, so things that can be copied cheaply, things that don't reference other data. You can still encode a lot of meaning in that using Rust enums, which is a lot of what I like about this approach. But it also means that the messages can serialize without dependencies or without copying variable length buffers. And it means that I don't have to worry about limitations in the IPC protocol interacting with path name limits and stuff like that, which just seems like it'd be a huge can of worms in trying to do this by passing the names over IPC. Yeah, that's interesting. Adler says that what they like about Rust Unsafe is that it's not necessarily unsafe code so much as an indicator that whatever you write there, you're on your own and you must know what you're doing in order to not crash. Yeah, that's a great way of putting it. A lot of people get kind of freaked out by seeing unsafe. I was in that category until recently. I kind of made peace with unsafe code for this project out of necessity. But yeah, it's not an indication that the code is unsafe so much as it's saying that the compiler in some key ways is letting you do things that it normally would not let you do, and that you're on the hook to make sure that the code is safe. I'm glad some folks are enjoying the Rust. Yeah, I feel like this is one of the nicer parts of computers at the moment. Yeah, I like a lot of, there's a lot of stuff that I can get away with in this sandbox process that feels really high level, but actually just compiles into some extremely basic low-level stuff in the end. So yeah, I like that a lot. So stuff like this, these match instruction or match blocks, where I can just kind of decode stuff, and I mean not these. This is just a switch statement, but stuff like this where you can match a type and then destructure that type as you're matching it. You use that all over the place, and just generally finding ways to encode your program's constraints in the type system is just, it always makes your life easier with Rust. Makes the compiler help you out more. So yeah, this is cool. Some of these are just IPC calls. Exec is the first place where I'm starting to do something significantly more than just an IPC call. I mentioned this a little earlier, but we went into a little bit of a side tangent looking at exec and talking about how its arguments can't really be validated safely because of time of use vulnerabilities. So, in a different universe where maybe Linux was very slightly different, there might be a way to safely use the kernel's loader, but I'm pretty sure that doesn't work, and we have to implement the loader here. So what this is actually going to do is load the binary. It's going to, take an existing process, remove all the state from that process, read a binary, read its headers, and then map portions of that binary into the process, and then restart the process at that binary's entry point. So just doing an old-fashioned loader. And luckily, Linux's loader is actually not that complicated. If this was Mac OS, we'd be having a much harder time. Mach O is such a pain, but Elf is pretty simple. The gotchas that we're going to hit with this mostly are, It's going to be weird to handle scripts and VDSOs. Um, so the VDSO is the virtual dynamic shared object. It is this thing that the Linux kernel maps into your address space during loading in order to help you implement some system calls faster, specifically stuff like retrieving the current time. It lets you do that without a system call. So I haven't totally made up my mind about whether we can pass through the real kernel's VDSO or whether we need to write a special VDSO for this. I don't really have strong feelings one way or the other, but it's also because I haven't looked into that as much as I'll need to. If we have to write a VDSO, we'd be writing it here in the loader, or writing it probably in Rust. I mean, I hope you can write a VDSO in Rust. I was looking at gvisor, right? And gvisor implements their own VDSO. Gvisor's VDSO is written in C. It's like everything there is written in Go except the VDSO, which they use, I think, GCC for. Which doesn't surprise me hugely, right? Like, I mean, especially with Go, like Go requires an entire runtime, and the VDSO like extremely has to run inside of other programs. Like it's not your own program. It's just a thing that has to run inside everything. It's also usually really little. Like I think on Linux, the VDSO is just a page or two. So it's not something you can put just a whole Go binary into for sure. It seems like I might be able to get away with writing it in Rust, but that's still maybe a little iffy. I'm still, I don't know how small it's possible to get a Rust program, but the VDSO just implements a couple of functions. I think on x86-64, it's mostly like get time of day and get current CPU number, stuff like that. Like really just stuff that does not require any privileges, just some data access, and just data access that doesn't require any synchronization. So stuff that, or not synchronization that requires trust. So like getting the current time, there is actually some synchronization involved in that. I haven't looked into how this is implemented on Linux, but I've looked pretty closely at how this works on macOS, and I think it's pretty similar on Linux now with the VDSO, where the kernel code in that VDSO, like in the shared object part, and macOS has a similar thing. I think they call theirs the shared page. They have a function in there for like get time of day or whatever. That first step is read TSC, right? Because like the CPU sort of knows what time it is. There's an instruction in the CPU to read the time. The problem is the CPU only knows the time in one format, which is CPU clock cycles. Which there's an asterisk there because of how CPU frequency scaling works, but there is 1 unit of time that it knows usually. There's an asterisk there too. I keep trying to simplify things and then accidentally telling lies. The main way that the kernel or the main way that the CPU represents time is available to you via an instruction called read TSC. And so just any code that's running on the CPU can just run that instruction and get some measure of what the time is. But there are some other steps you need to do to convert that into a time that anybody actually wants to use, because that CPU time measure doesn't take into account things like the CPU going to sleep or changing speeds or wrapping around. Going to sleep and changing speeds are like a big deal. Like the macOS code I was looking at in more detail about this, it seems like they were kind of early in the game of trying to like really robustly support CPU frequency scaling on a Unix-like operating system, and so like they had a lot of code specifically to handle that in like get time of day. But because it doesn't need to live in the kernel, all it needs is read TSC and some parameters that it uses to scale that value. So anyway, that's like a rabbit hole, but that's what the VDSO is, and I may or may not have to write one as part of this loader. What else does it map? Like part of why Linux's loader is pretty simple is that a lot of the work is done after the kernel loads the process by the dynamic linker. So on Linux, and I think on a lot of Unix-like operating systems, the dynamic linker is a separate piece of software from the kernel. So the kernel knows how to run a process, but the kernel doesn't actually know about dynamic libraries, which is actually like partly why it's so conceptually weird to me that the VDSO is even a thing. Because like shared libraries are kind of not the kernel's domain at all. But I need to look at how this works closer. I think the VDSO is only sort of a real shared library in that it's like linked into your like elf headers by the kernel or something, but like it has no relocations or anything. So it's like much simplified compared to loading kind of an arbitrary shared library. And the arbitrary shared libraries are loaded by ld.so, the shared library loader. And that's just a program. I mean, it's a shared library also, but it's a program. And so that's going to be one of the first things that I have to run inside the sandbox. Like, when I'm running the sandbox, have I even run this on stream yet? I feel like I've run it, but I haven't explained, like, yeah, so I mean, here it is running, but I don't think I actually mentioned how far this is getting, because it wouldn't make a lot of sense without that context. But now you can see that this is actually downloading the container, but I have the debugging for that turned off, so it's not showing up. The debugging is starting out kind of showing you messages going back and forth to the sandbox once it's already kind of going. So we've got some messages going back and forth. There's this open process and open process reply, which are the messages that we were just looking at a little earlier. And it replies with a process handle, which includes file descriptors that map the memory and the list of maps. And sending those over the IPC channel actually transfers a copy of those files into the tracer. Then we do a sysaccess here, which is mostly stubbed out. This is so the point at which we start is a little weird here. So the very first thing that happens in the task is that task function starting and then calling the constructor on that task object. This one. So if we wanted to follow along over here, so we've got the task constructor. This ends up starting up pretty much as soon as we know what the process's process ID is. So, and the process we're tracing is not running this code. This is running in the tracer. So the trace E is, oops. I always forget how to like close individual windows when I split the wrong one. Oh, trace E. I've been calling the trace E the loader. I don't know. I feel like those terms for me are kind of interchangeable right now. I started calling this loader because it seemed like it would be the thing that loads the process inside the sandbox. But its definition of loading the process is really just calling exec and letting the system call emulator do the actual loading. So I don't know if it makes sense to call this the loader. But anyway, this is the child process starting up. So yeah, actually the first place that it probably makes sense to follow along from is when we do the fork. Oh, where was the fork? That was in tracer. Yeah, tracer run, tracer spawn. Okay, tracer spawn spawns a new process by forking. We're going to be, oh, we haven't looked at be the child process yet. That's kind of important. Oh yeah, I'm not calling get event message yet because that is necessary for fork, and I started to implement fork and then I stopped. Oh yeah, be the child process. Yes. So this function and the task constructor are kind of parallel with each other. The child process is starting up, and then the task is starting up the process of tracing it, and the two kind of collaborate for the startup process. Oh, hey, Tuco. Oh, I was going to try to bring cat cam back, but the camera's asleep. I like how with this green screen setup, it looks like I'm really tiny and Tuco's huge. Aw. What a sweet cat. He really likes this cardboard cube. Got this for him earlier this year, and I've bought him plenty of cat toys where he's not really into it, but I like how into it this one he's been. You can tell just by like how destroyed it is at this point. He also really likes that wheel, but he's super fickle about it. He hasn't been using it a bunch recently. I don't know if I just don't have it set up in a good location, or if he's getting older and doesn't like it as much anymore, or if it's the weather or what. But he hasn't been running as much, but he loves the cardboard. Oh, what are you doing, Tuco? Oh, I was absentmindedly taking the wrapper off this chapstick, and I think Tuco likes the plastic wrapper. Gotta rub your face on it. There's a question from a Twitch chat, executor question mark. I'm not really sure what you mean by that, but I guess the thing I'm writing is sort of like an executor. It's like a... You mean like an OCI runtime executor kind of thing? There's a lot that this has in common with that. I'm not trying to make this actually follow the OCI executor standard, but I am trying to make it work with OCI compatible images. I feel like, there are already plenty of projects like gvisor and runc and crun that are trying to be good OCI runtimes. I'm trying to do something which you can run containers in, but it's really designed as a library first. So it's mostly intended to be a thing that is easy to run embedded inside of another application. So you can link with it as a library and then just use it to make little sandboxes that you can do specific tasks in. And the use case that I mostly have in mind for is media transcoding. So you can make a little special purpose sandbox just for doing a transcode and then throw it away. And so I've been mostly just talking about the architecture of this thing so far. I haven't been like coding and debugging on stream, but I've been on just like a big coding binge for a couple of weeks now, or I don't know, time doesn't really exist at this point. And I feel like it's been nice just getting a bunch of architecture out of my head and onto the repo. And this stream so far has mostly just been kind of talking about it and sharing it with all of you. And cat appreciation. Aw. I so like it when Tuco visits us. Oh no. He is in a very biting mood, and if I get my finger in the wrong spot, he's going to hurt me by accident. Oh, don't swallow any of that, honey. Let's take that off. Cat slobber. Oh, honey. Does it smell interesting? I was at the bargain grocery store buying groceries recently because sometimes they have interesting stuff. And they had like the bargain chapstick, which was a multi-pack that was mostly unflavored, and then one really strong flavor that I think a lot of people don't like, just like a coconut or something. That's what this is. So maybe Tuco's sensing the strongness of it all. Cats, yeah, a lot of cats do seem to like eating plastic. Tuco's certainly one of those. I think a lot of it's about the texture, but some folks have also theorized that there's like something about the taste or scent that cats like too. Tuco seems to really be into just like kind of crinkly stuff, classic cat things. Oh yeah, that's a good theory. The Orb2 from Twitch chat says that it's probably like leaves crunching under critters scurrying in a forest. Yeah. Oh, he's so purring now. I wonder if I can get any of that on the mic. It'd be easier for me to do this with headphones. Trick is to get the mic close enough that you can hear him purr without him eating the mic. Cats are so good. I mean, cats in general are so good, and then Tuco in specific is just really, really nice. This is also a better camera than I usually have for Tuco. This is like my new DSLR that I got this year, late last year, pretty recently. It's got a few more pixels than the usual Tuco flare. Aw, he's like cooing. There's this YouTube channel that I don't know. It's like a veterinarian in Canada that has a kind of a cat appreciation channel, and they have this T-shirt that I bought that says "Squish the cat," because a lot of cats just like really enjoy kind of like pressure, like being hugged or kind of having a little bit of squish. And I can relate. Like, I feel like if someone much larger than me were doing that, I'd be super into it. Cat massage, right? Oh yeah, unsafe as the lands of sea. Yeah, no, that's also another way I think about unsafe in Rust is like, when you're writing unsafe in Rust, it's still safer than C code, and I'm used to writing C code. But I mean, I'm also used to C code requiring just either huge amounts of documentation about what specifically you have to do to make it safe, or just a bunch of YOLO kind of cowboy stuff where people write code and just debug it when it breaks. So like, neither of those are great. One just requires huge amounts of research before you do anything, and the other involves like writing a bunch of bugs, and specifically writing a bunch of security bugs. Yeah, I feel like Rust is a pretty great language for this particular project, because if it was in anything much higher level, then it would either be difficult to do the kind of in sandbox half of this in the same language, or I mean, gvisor gets away with doing a lot of this in Go, but I mean, part of what you give up with that is that it's not like a library that you can just that you can like import anywhere. It's like a whole separate binary, and you could embed that binary. But even if you start kind of going down that route and start trying to build like, oh, what if I wanted to build a Rust library that just like wraps gvisor and tries to make it easy to deploy, which is certainly something I've considered, and I don't feel like I've completely put that off the table. But that seems like it would be just like a lot of complexity for something that doesn't have to be quite so complex. And then it would also, just in the general case, require some system level configuration. Let's see. And I think a lot of that does come from like the container ecosystem that's built around having containers exist in the real file system. So like my understanding is that stuff like runsc and runc and gvisor, like even gvisor, like architecturally gvisor has its own file server. I like one architecture I've thought about doing is like, well, if I wanted to make an embeddable gvisor, what if I took parts of it, compiled it in, parts of it left it out, and then implemented like a Rust version of its Plan 9 file server that's in the component they call a gopher, which is sort of like my runtime. It's like the more privileged thing that handles file system access on behalf of the less privileged thing. So I could imagine implementing that in Rust or whatever, and then doing the same virtual file system and kind of stream attaching stuff. That might be one way to do the architecture. I mean, I feel like if I hit any kind of like really significant roadblock in this approach where I'm just trying to do it all myself, then that might be a good plan B, is try to use portions of gvisor, like the interface gvisor provides. Like it's designed to be just like a single thing that you can just build and use, right? It's not like a library. It's a binary which implements the OCI container runtime spec. So the idea is that you compile it, you install it on your system, and then you use it as part of an existing container orchestration system, which is nice, but also not what I want, because like I specifically want a library that you can embed into other apps. Oh, hey, Duke. So yeah, one way to do that might be use some portion of gvisor to build a library, which might consist of a Rust version of the Plan 9 server, and then an embedded copy of the gvisor kernel emulator binary, which they call the Sentry. That might be one way to do it. Whoa, hey, Tuke. Oh, you want that again? Oh yeah, Squish Your Cat. Yeah, other people have heard of that. Yeah, I think the actual name of the channel is something like Helpful Vancouver Veterinarian or something like that. Chuko, why do you like chewing chapstick tubes? Aw, now he's just licking me. Tuco is so shedding right now. Hey, little guy. Streaming computer is going to sleep because I'm petting the cat too long. I've got to turn that off. Sorry, I just saw that comment that Tuco clearly wants luscious lips. Aww. Oh man, I think Tuco just likes having a spot to hang out that's right next to here. I think he gets stressed out when he doesn't have a good spot to hang out in. That was a weird noise. I feel like I should switch back to the computer, but maybe make Tuco small so we can still see him. Oh yeah. Sometimes I actually remember to use OBS Studio mode to make it a smooth transition. All right. I think I was mostly just going through these two sides of it where the child process is headed out to do trace me, wait for the tracer to stop, and then exec. This definitely needs changing because none of this is supposed to have access to real process IDs. So I need some other mechanism to allow that other process to attach. There's a lot of ways I could do that. I could intentionally cause a seg fault, that doesn't take any privileges. So I just haven't gotten around to doing that yet because it's still kind of on the to-do list to lock down the system calls a little bit further. But yeah, that's mostly what we're doing is we start the trace, we have a sig stop, and then exec. That's basically the program we're running right now. And then exec is where we're trying to be a different program. So the first thing that we exec here is actually the loader process, which is the same binary as sand. This is over here. And all we're doing here is setting up setcomp and then calling exec again. So from the tracer's perspective, it sees the process. Well, so it doesn't actually see the process fork off. That just happens. The tracer attaches as soon as we do this ptrace trace me, but the tracee does not actually stop until we do this. So at this point, this is the first event that the tracer gets. And so that has to be the first event that the task responds to. And that's what this is. So ptrace set options is just a way to tell ptrace what things we want to stop on. It doesn't have to come before this event. It just seemed like it could go first, and that would be a handy place. And this is kind of how we're synchronizing with this process. So this process stops right here, and then while this is stopped, simultaneously the other process is running and getting this ready. and this will be blocking here until this actually happens. If things happen in the other order, like if this process stops before this actually reaches this point, then that event will just be queued and we'll still process it first. It could be queued either by the event source here or by the kernel, depending on exactly how the two processes line up in time. And then we run it, and exec. I feel like this shouldn't actually be here. We're handling the signal that ptrace generates when we did this exec. So oh, that's right, because we don't have this is while exec is actually still allowed by the setcomp. So when we're in the tracer, the setcomp profile has not yet excluded exec. It will be by the time we reach the interior of the sandbox. But at this point, exec is still allowed. So this is a real exec to exec the loader process. So last real exec will do, because the first thing the loader does is it puts in a more restrictive setcomp policy. So this is a real exec, which should happen only once. So I think this is actually fine to be here. I was thinking this should be handled as part of the main event loop, but we are synchronizing with the one real exec that will ever be allowed, and then and then at that point, I do think we will need to handle some additional ptrace events for forks, but most of the events after that point are emulated system calls from the setcomp trap. I need to go. Are you finding some wires to chew on? Tuku is in a very weird spot. He's like sitting on a pile of wires behind the chat stream here. Someone on Twitch is asking if my hand hurts. I have no idea what you're talking about. I mean, yeah, typing is not the easiest thing. I actually have like an ergonomic keyboard that I've been trying to use more, but I don't use it on this particular setup. Tuco is slightly off camera, and I don't know if I'm going to move the camera, but he's being cute. I can't tell if he's done walking yet. Oh, do you want this back, Hugh? He might just be still following the chapstick container. I put it back where he was just sitting, and now he's looking at it intensely. Oh, Duke. Actually, I feel like the Emacs setup has been really good for just like reducing the extent of my bad keyboarding habits. Because by default, Doom Emacs enables Vim emulation with evil mode, which I have mixed feelings about, because I feel like I'm a little more used to the Emacs key bindings than Vim, honestly. So at first I tried to disable it, But it seemed like Doom Emacs was breaking if I tried disabling evil mode because of some probably bug, but I didn't feel like debugging it. So I just started trying to get more used to the Vim key bindings. I do use Vim some, but not as much as Emacs, and so getting a little more used to it was kind of nice because it does actually hurt your hand less. But I'm still using just like a weird mishmash of different strategies at the moment because that's what I'm used to. But yeah, mostly I can hide the mouse cursor under myself and just use the keyboard. So yeah, once we're in the task here, then we're mostly just in the system call processing loop again. Gosh, I feel like I've talked about most of the interesting parts in this so far, except for the actual inter-process communication protocol. I know I've skipped a bunch of things though, so if there's like something specific that folks want to hear more about, I'm happy to talk, but I could also go back to just like trying to debug things and write code. Oh, where were we? Oh yeah, protocol. This part is kind of weird. I feel like ideally this would actually be a separate crate that both the inside and the outside of the sandbox depend on. I've just been having this weird setup with the Rust build system because I want the inside of the sandbox to be a separate workspace so that it can have different compile options. So the way I'm doing this right now is that this is just a file that is like macro included by the exterior of the sandbox. Yeah, just this whole thing. So this is outside the sandbox in the runtime. It's just getting a binary blob of the program data, and at the same time, it just has a little module here that include bang protocol.rs. So it looks a lot like the same code is just in both projects, because that's basically what's going on as far as the compiler is concerned. It would be better if I was importing this via the module system, but you know, this gives me a pretty similar outcome. So I do have a bunch of Cerdy in here. So I'm using the serializer deserializer framework for Rust called Cerdy, which is just a pretty nice like layer that you can use to serialize data and to define serialization formats. And it generates pretty nice code at compile time usually. So you just get strongly typed data, and you get pretty much arbitrary serialization formats, and Cerdy kind of helps you bridge those two. So these are the main types that I'm passing back and forth. So when I send a message over the IPC channel, I'm serializing one of these two things depending on the direction of the message. These are basically the same, except that they have different messages. It would certainly be possible to make them the same type, but again, this is one place where it seems like I can use the type system to help me out more, and by making them separate types, then I'm not allowed to kind of substitute a message into a communication channel that's going the wrong direction. All the messages have an explicit directionality to them. So the message wrapper here includes a specific task always, and that's because the actual delivery of this message needs to go to a particular queue, and the queues are all per task. But then the message contents are pretty much arbitrary. This will just be, I mean, again, there's a bunch of data types that I'm not allowing. I'm not allowing variable size byte arrays. I'm not allowing floating points, not because I have to, but just because it doesn't seem like I need them. But most Rust types are supported. And I feel like this is like the best part of this file. Like you can return a file or an error, and the type system and the serializer both understand that. Like There's none of this thing where you're returning a number and someone later on has to decide if that number is really a file or an error code. And if it's a file, you need to actually confer rights to the file, whereas if it's an error code, you don't. And so like those are fundamentally different data types with completely different transportation requirements. And so it's nice to be able to use Rust's type system to represent that. So if you send a file open reply that is an error no, so if it's this result is a Rust type that's really just a very simple variant that can be either an OK or an error, and it has different types for the OK or the error variant. So in the event that this is OK, the type is a sysfd. In the event that it's an error, the type is an error no, which is just a thin wrapper around a uint, or sorry, an int32. So, most of these are just like pretty basic types that we're asking Serity to automatically generate serializers and deserializers for. But sysfd is a place where I can handle it specially. So when you encode a sysfd, this represents a local file descriptor. And when you send it across the communication channel, when it comes out on the other end, it will be a local file descriptor that represents the same kernel object, but has a different numerical value because it represents an entry in the process table for the remote process and not the local process. So yeah, anything that you can represent as a Unix file or like a Linux file, you can put in a sysfd and pass through one of these messages. So I'm using that for actual files, also for some of the stuff in /proc. So I don't know. I would like to split this file into the protocol and then the serializer, because those are conceptually kind of different. But right now it's monolithic because of the way I'm doing this include. It's kind of on my list of stuff to rethink. Like I want to find a way to make this like an actual an actual crate or module or something, and not just a single file. But the way it is right now, all the code that needs to be shared is in this one file because of this limitation over here. Oh, Tuco, you're still playing with that, honey. Hey. Oh, more cat time. Oops. Ow. You just want to be over there. You happy now? It's on the floor. You just want all the objects to be on the floor. I tried a bunch of things to get this serializer to work, because I didn't want to have to write a whole serializer from scratch. There are a couple of existing. So I mean, just for a little more background. So Serity is a whole serialization framework. There are very commonly used serialization modules for things like JSON, YAML. All the common formats work with Serity. There's also a pretty nice serializer called bincode, which is a fairly simple, non-self-describing binary format, which is kind of like if you just took like the raw C struct representation of some data and put that in a buffer, but you actually tried to make it portable. So it's not, if I'm remembering this right, I don't think bincode has the ability to like version things itself, but it has like a more compact binary representation and better like padding and alignment kind of properties than just like copying the data into a buffer in its native format. And then there's stuff that goes like even further, like protocol buffers actually are not super Serity compatible because of actually this might have changed. I was reading something that said that protocol buffers. It was somebody's protocol buffers library for Rust, and they were saying like, this doesn't work with Serity because in Serity there isn't a good way to add like annotations to the specific fields to indicate like what their which constant they're all defined as. Protocol buffers doesn't like automatically assign enum values or struct field values. Those are part of the protocol specification. But I don't think that's true anymore. I think SerDes actually could use Rust attributes to assign those. So I don't know. Maybe there's a way to do protocol buffers in SerDes now, but at the time I was looking at that random library, there wasn't. Oh, that's a good question. Slash Attack on Twitch is wondering if a cargo workspace would help. I'd love it if they would. I actually had to explicitly make the sandbox not be part of the same workspace as the runtime, though, because they need different compile options, and also the inner sandbox process needs to be fully built before I build the outer process. So I'm not sure how to make those requirements work with cargo. So the way I'm doing it right now, they are separate workspaces, and I'm actually using a build.rs build script to run a nested invocation of cargo. It's really bad. I would love a better solution for this if anybody knows a better way to do this. Let's turn the cat cam back on, sorry. Yeah, so I've got this build script in my outer project that it just runs cargo in the build script. I don't like it. I would love a better way to do this. But yeah, I need separate compile options, and then it's like under the cat right now, this other window. Yeah, so right now this is my build script, and then this is like the reason the build script is like that is because I have this file in the outer module that just needs to include the entirety of the inner binary. And there's a different way I could do this, like, well, I'd solve one of these problems by just having the sand and the runtime be two different binaries in the same crate, and then having, like, not doing the thing where I build one into the other. I like that for convenience, though. Like, I like having no external file system dependencies for the library. Like, I would find it annoying if I was using someone's library and they said the library only works if you have a specific file installed somewhere. So I'm trying to avoid that. But that's a part of the project that's pretty easy to change. Like, the way in which you package and run the sand binary is not like really intrinsic to the architecture. It's just something I'm trying to do in the most convenient way possible. Oh, somebody's like, yay for file descriptors being integers. That's not Rust, that's me. Like, so just to be clear, like, Rust has some very nice high-level file interfaces, which I am not using in this project, at least this part of the project, because it does not use the standard library. And that's because I'm not using the C library, so I can't easily use the Rust standard library without the C standard library. But yeah, if you look at the code that's outside the sandbox proper, like, it uses like plain old Rust files. In fact, I think we saw some of that in the IPC server for handling. I thought there was something file related in here. Oh yeah. Actually, that's not the example I was looking for, but this will work. This is my current implementation of file open, which is just a stub. But so we haven't actually gotten to an open that matters, but I was doing some earlier debugging where I was just trying to like skip over an open and get to something else. But I was also using that as kind of a test bed for the file descriptor passing. So this was actually the first file descriptor I passed through the IPC mechanism. I just opened dev null on the runtime and then passed it through. But yeah, normally in Rust you work with these file objects, and you'd have to call as raw fd to get the integer out of it. The thing I'm doing in the sandbox where I'm mostly using files as FDs is because I'm mostly using files as like kernel objects and not as like streams. So yeah, it's more like using like handle in Win32 or something like that. It's like probably not what you do in an actual high-level application, but if you're writing like low-level Win32 code, then yeah, you're gonna have handles. So yeah, the protocol. So the actual protocol proper is just this section up here that defines a few messages and isn't even very much yet. Once we start going into buffer, so we've got a couple of implementation pieces. So buffer is the only public submodule here, and then it publishes error and a couple of other structures. There's like an IPC buffer, an IPC slice. And then IPC buffer is conceptually a pair of double-ended queues. So it's kind of like you had a double-ended queue that could hold bytes and files at the same time. It's really designed to be easy to use both as a storage for the serializer deserializer, because they both operate on this using stuff like, pushback file and extend bytes, these kind of interfaces. But then you can also just take this entire buffer and use it with send message or whatever. So you can get so first of all, you can put it into a state where the whole buffer is clear by setting the offsets to 0. And you can unsafely set the length of the buffer. And you can get a mutable slice representing the contents of the buffer. So with those operations, you can do both pretty low-level and pretty high-level things with this data type. So that's like the main representation I have of a serialized IPC message is this buffer. And then separately I have the serializer and the deserializer. So yeah, I tried a bunch of different things for these. I think last time I streamed about this, I was using this crate called SS Marshall, which stands for super simple marshalling, I think. Which is just a very simple like value type or like a serializer that only works with value types. And then on that stream, actually, someone in chat mentioned Postcard as another serializer crate should check out. And I appreciate the recommendation a lot. I looked at it some more. At first, I was kind of annoyed by the type num and heapless stuff in it. But once I got more used to that, I actually kind of started liking it. And yes, I wrote a whole bunch of stuff around Postcard, actually. At first, I was using Postcard as my serializer for messages that didn't include files. And then I went down the route of trying to wrap wrap Postcard's serializer in my own serializer. So I'd have basically a layer that would forward most things to it, and then have special cases for file descriptors. That just got too complicated, though. I don't know. I learned a lot about Rust macros and traits in that whole process, but the thing turned out to be both complicated and not good in that I got the serializer working going that route, but I hit a wall when I was implementing the deserializer, and I couldn't find a good way around that. And I started coming up with like even more complicated workarounds for the deserializer issue until I realized that my wrapper was already approximately as complicated as Postcard, and so I just started writing my own serializer specifically for this. So yeah, now I've got this little special purpose serializer and deserializer that work for these IPC messages. There is still kind of one grossness about this based on how Serdy works, which is that I do have this like magic string that you might have already noticed. This does not have any meaning outside of this particular module's implementation, though. It's just a way to communicate between the serialized trait implementation for sysfd and the serializer itself. So like part of Serdy's strength, and also like I guess the weakness that I'm hitting, is that they have a very specific data model that all your serialized data has to fit into. And it's pretty much just a mapping of Rust's primitive types into something that you can implement as a trait. So just to be slightly more concrete, that's where stuff like this happens. You get like serialize bool, serialize various integers, serialize unit struct, serialize string, serialize unit variant. Like these are all basic Rust data types, and Serity defines a way to map all those different Rust types into function calls and objects that form a protocol that you use to serialize those types. It does not have entries in that protocol for every specific instance of a new non-built-in type, though. So like the Serity protocol knows about structs, but it does not know about each specific struct. So Serity is, in this case, sysfd, the type I'm implementing here. So the actual type here, this could be whatever. This is pretty arbitrary, but just for convenience, I made this a tuple struct, is what Rust calls these. So it's like a struct that has unnamed fields, and it's useful when you just have a couple of things and they don't need to have a separate name. So it's basically just like a really simple struct that wraps a uint32, but the important thing right now is that this is a struct that I can implement serialize on. So when that starts to get serialized, instead of going through, whatever serializer that Serity would automatically generate for this, which would just say I've got a tuple struct with one thing in it, whatever, I am generating a special purpose serializer. This is actually very similar to what Serity would generate. In fact, I might be able to get the same effect by just customizing the name of the tuple. But I wanted to specifically make this a bit of an out-of-band channel, so I'm using a string here which is not a valid Rust identifier. So I'm not sure Serity would let me do that. And even if it did, this seemed more explicit to just write the trait implementation because I'm depending on it so carefully. So what this does is it starts making a tuple struct, but then it uses a name for it that is this special string that is not a valid identifier. And that special not valid string gets picked up down here when we're actually serializing tuple structs. Yeah, and so we just set a flag that has some state indicating whether the currently serializing tuple struct is a sysfd or not. And then when we're serializing the uint32 inside the sysfd, we can take a different path and add it to the file queue instead of the byte queue. That's the essence of it. Like, that's really the core of this. The rest of this is just because I needed to write the whole serializer myself. So it just has... I actually wrote a macro to do most of this, and so I don't know why Postcard didn't take this approach, but a lot of the basic types, you can just call 2 little endian bytes to get them to serialize themselves. So any type that supports that, which is just all the built-in number types that aren't floats, you can just serialize them with this macro. But then, of course, the complicated data types are complicated. So the way Serity manages this is that when you serialize a more complicated object like a struct, you start serializing it here, but then you return an object that finishes the job. But the way I handle this and the way Postcard handles this is that in this case, I'm just returning self because I'm implementing those interfaces on the same object. So all of these are the same kind of object. And that same object also implements traits that handle the interior of tuples and structs and variants and whatever. So when something like serialize tuple gets called, this doesn't have much work to do. It just returns self. And then the caller sees that as not the same object necessarily, but as this serialize tuple struct thing that we asked for. And then we can go down and use the implementation of that to write the contents into the serializer. And then there's sort of another level of indirection. No, that's not here. That's entirely how this works. This is the actual value type, and this is it actually getting serialized. So this is then the serialized implementation for this particular type. So it's using the Rust type system to dispatch this to the serializer for the correct object type, or the correct type, like according to whatever this is. So in this case, like for the interior of sysfd, when we're inside of the sysfd tuple struct over here, this value would be a u32, but we can't actually access it directly as a u32 right here because This is generic code that is written to assume that T is anything that is serializable and might not be sized. So this is a trait bound that tells Rust for a generic type here which types are actually acceptable. As a consequence of that, the code that's in here, you can't just call like arbitrary methods on this. You have to use this through the window of these particular trait bounds. So even though I know as a programmer that when sysfd comes through on this path, it will definitely be a U32. The code here has to be implemented in a way where it can accept any serializable value without actually knowing its type. So that's why we have this other layer where it has to serialize itself. Then that kind of comes around and calls the serializer again, and we end up back in serialize U32 up here with some state that indicates that's what's going on. There are probably, I was trying to do this without the local mutable state here, and it seemed like in these functions that return self right now, I could return a different object. I was trying to make that at first just another instance of this same object that has a flag set so that I wouldn't need to like physically duplicate the code or macroize this whole thing. But, oh, I bet I could make that a type parameter. That's kind of what type parameters are for, right? Like I could have a type parameter so that I don't know if that would solve the problem though. The problem I ran into when I was trying to do it that way is that when these return self, if I remember right, that's not actually an owned value. That's a mutable reference. Yeah. Self here is not an IPC serializer. Self is a mutable reference to IPC serializer. So by returning self, they're not returning a new object. They're returning a reference to an existing object. And if I was trying to make a new object, like there'd have to be somewhere to put it, right? Like I can't just return a reference to an object that I've not stored anywhere. So that was the problem I ran into. And again, because we're not allocating memory, I can't just allocate memory, but like it would still be good practice not to allocate memory for something like this, because I'm sure there's a much better way to do it. I would rather have a mutable flag on my one serializer than keep allocating a bunch of additional serializers, right? So that's how the serializer works. It's relatively simple. It mostly just has to have a lot of code because it has to deal with all of the Rust basic data types. But it works very similarly to postcard or bin code. It's actually maybe a little bit more like SS Marshall than postcard. Postcard tries to support strings and variable length data types, whereas I'm explicitly not supporting that because I don't want them. And I'm also using a single byte for variants, whereas postcard uses variable length variants. And that's just because I expect this to be small and to not have more than 256 variants, and I don't want the complexity of variable length variants. Yeah, so I think the deserializer is a little bit more code, but it has a similar job to do. So it has a deserialize implementation, which is specific to sysfd. Deserialization in Serity just overall seems a bit more complicated than serialization. Deserialization goes through this process where you have a visitor, which is in a type. What is the visitor specifically? The visitor is a value that knows how to fill in members of the output type that you're deserializing to. So the idea is that you would create a visitor that references the output of your deserializer, and then you call the visitor with each of the particular kinds of objects that you have, and the visitor would store that somewhere. So normally the visitor would take that integer or whatever and just return it as an integer. But in this case, this is my opportunity to take the U32 and wrap it in a sysfd structure. But this can't actually read the file queue. So like the deserializer is like conceptually on the other side of Serity's interface boundary from, or sorry, the deserialize implementation is on a separate side of that boundary from the deserializer. And so we have to kind of get things through that Serity protocol And so again, I've got this like weird string that I'm using. And that comes in down here. So this visitor is actually a type that we're creating inside of this function, which is like a little bit weird if you're not used to that, but I thought it made more sense for keeping the scope restricted. So deserialize is the deserializer implementation for sysfd. All this really does, though, is it calls deserialize tuple struct, just like the serializer did. But because we need a way to sort of fill in the results of that deserialization, it has to provide one of these sysfd visitor structs, which gets callbacks with the actual contents. So sysfd, this magic string here, is how we're signaling to the deserializer that we want this to be special. We don't want this to be a normal tuple. But then this can't do anything special to get the value. It still needs to sort of deal with a normal, like this still looks like a tuple struct containing a single U32. Oh, actually, I did simplify that slightly. If this was a tuple struct containing yeah. Normally the way deserialization works is that this visitor would actually get a sequence first, and then the sequence would contain a U32, because the tuple struct has... I don't know if that's actually true. Yeah, this is something where I haven't looked into how this normally works in SERD, because I'm doing things slightly weirdly. Normally this would either be the contents as a U32, or it would be a sequence containing a single U32. But because I'm doing this special thing with my kind of weird object here that is not normal, but is kind of indicated to the deserializer as being abnormal through this type or this string that isn't a real identifier. Because that's happening, I can decide that whatever happens inside this visitor is now special also. So this doesn't have to follow the normal deserialization protocol. I can just decide that you're getting exactly one number and it's just a file descriptor, and you get to put that in a tuple. So then the rest of that happens in the deserializer, which has something... Oh, yeah. So in addition to the visitor, the deserialization also has these access objects. So kind of similarly, like the deserializer here, it needs... is this constructed around the visitor? It is confusing that this is also using v as a type parameter. This is a shadowed type parameter. I shouldn't be doing this. It's not incorrect, but it's unnecessarily confusing. This is the deserializer seed, not the visitor. I was using v for visitor. Let's use s for seed rather than d for deserialize. This is getting into really esoteric SERD internals, but deserialized seed is a optional type that, like, you don't have to use it if you're using the deserializer, but you can optionally use a deserialized seed if you have a stateful deserialization that needs some additional data. The only place I use it is here, because you're required to take this for the... sorry, I'm not describing this very well. This trait that I'm implementing, sequence access, it provides an API that doesn't use deserialize seed, but uses a higher level interface, which I think is just called deserialize. But because we're implementing this, that wrapper is provided by the generic implementation of the trait, and we have to implement the more specific version of it and get the generic one forwarded to us. So this is just SERD internals that we don't extremely need to care about, but we have to get right at least. Oh yeah, and I've got to change this. So the idea is this is an object that this is a struct that that deserialized tuple will pass into the visitor as sort of a source of multiple elements. So So all these deserialized functions get called to deserialize a single value. So if it's a primitive type, that's pretty simple. If it's a tuple, you're deserializing a value, but there are multiple additional values inside that single value. So yeah, I think the way this normally works is that inside of a tuple, as far as the SERDI data model is concerned, there is this other thing called a sequence, which I think can also appear on its own. And so visitor visit sequence tells the visitor, which in this case is like a structure that's wrapped around the tuple that we're deserializing into, and it tells that visitor, okay, I want you to store everything from a sequence. And then the visitor will visit all the items in that sequence, which is cool, except the visitor needs a way to get those items. We don't want to just give it a list of items because then we'd have to copy them. We want to give it a way to access the items one after another. So that's what sequence access is. So it's sort of like a callback, but it's like a type that we're passing as a callback. And so this holds a reference to the same deserializer, but it also keeps track of some state, which in this case is like how many elements are left in the tuple. And we can just pass each of those interior elements onto the deserializer. This is not at all special for what I'm doing. This is like basically the same implementation of this you would see in most very simple deserializers. It's just something that needed to be done. So it's like most of this file. Yeah, and I've actually got tests. So I did a bunch of tests for various data types to make sure that they serialize and deserialize correctly, and they give you the right bytes. And like a lot of test cases, I feel like this is the best introduction to what this code is actually supposed to do. So if you look at the non-macroized test cases, you can see like you can make an IPC buffer, and you can push messages into it, and you can pop messages out of it. That's basically what it does. These two don't use files at all, but then we have a test here which encodes some like more substantial messages. So this is like the heart of it. We want to be able to serialize several file open replies, some of which were successful and some of which weren't, and then deserialize them and just get that back. And nothing outside the serializer should have to know that, like, oh, we had an array of 3 files that mapped to this message, and that message and that message. It means that outside the serializer, we can just treat the files as if they're fairly normal types of data. And then I wrote some macros to do the repetitive tests. Yeah. I was pretty happy with how this turned out. I might end up having to hack on it some more, but I feel like this is a pretty solid start for an IPC layer here. Let's make sure that compiles. What if the deserializer deserialized the data extra much? I mean, there's an error for that. There's an error for everything. Yeah, file types are nice. I might try to make that sysfd type a little nicer, since right now it is pretty low level and easy to mess up, and like it doesn't keep track of file lifetimes at all. It doesn't close files. So I might want to do something that's more, what is that the C++ folks say? RAII, resource acquisition is initialization. We could do a bit more of that and have sysfd automatically dup and close files. I'm pretty sure the sandbox gets access to duplicate file descriptors. I don't think there's any harm in that. I'm definitely going through the kernel source code for all the syscalls I end up allowing once I'm a little further along, though. Haven't quite gotten to the point of doing a severe audit. Okay, that is That is as working as it was before. Yeah, so we're trying to do a loader. Let's go a little further in the loader. Okay, so we've seen the syscall layer where we have files and IPCs and whatever. But then there's the loader. So exec. I'm not totally sold on this strategy yet. I might change this, but right now, okay, so to back up, I need a way of processing, I need a way of passing arguments into the container. So I'm still trying to run the entry point process. Oh, I guess Tuco left us. I'm still trying to run the entry point process. The entry point starts out with arguments that come from outside the container. So I need to pass those arguments into the container somehow. I just generally don't want to be passing arguments over the IPC channel because I don't want to be passing variable-sized data over it. I don't want to be passing anything that requires allocation or arbitrarily large buffers. It should only be for small value-only messages that fit in like a couple hundred bytes at most. So I don't think there's any world in which I'm sending the actual process name arguments or environment variables over the IPC channel at any point. That makes a lot of sense, right? This IPC channel is kind of analogous to how system calls work in a regular kernel. And in a regular kernel, system calls don't natively transport strings. They just transport pointers to strings. And then the kernel uses memory mappings to actually get the data. So I'm thinking about doing something similar here, where the arguments and file name and just anything else that we need to start that first process, they would come from outside the sandbox, but via something that's more like memory flavored. I've also considered passing them through the outer layers, or sorry, through that stage 1 tracer process that gets run first. So if we go back to the main in the sandbox, it gets run twice. It gets run first in this tracer mode, and then after setting up the tracer, it runs itself in this loader mode inside the tracer. So the tracer gets some command line arguments. It gets an environment. We could keep the entry point arguments inside that, like have them nested somehow. I just feel like that's kind of a security hazard, though. Like, if that isn't done correctly, it seems like there could be problems with exposing either environment variables or arguments to the outer process. Which, I mean, to be clear, the outer process mostly does not care about any of this. Like, it looks for one file descriptor and then ignores the rest of its environment. But when I was thinking about doing this, I was thinking about like, okay, I need to have a way to embed one set of process arguments in another set of process arguments, and that just did not seem like the reliable and secure way to approach the problem. So maybe I'll rethink that later, but right now my thinking is that I want to keep the actual system parameters, like the argv and envp for the process, just completely stripped down to never let the sandboxes env and args touch the real kernel, and to just do that entirely virtually. So I think what that looks like is at some point during the execution of this loader process. So, I mean, well, we can see it right here. Like, this is the exact point where we would really like to know what arguments to pass to the next process. And we don't have them here. We have them in the runtime. We can't talk to the runtime from inside here. Like, this is the tracee process, which does not have an IPC channel. All we can do are emulated system calls here and a few real system calls. So the setcomp policy loader thing is, or policy for loader, those are real system calls that we are allowed to do. but then that exec VE is an emulated exec VE, which lands at the top of the screen here. And maybe there's a better way to do this, but my thinking here is that there can be a special case in exec where if you pass it all zeros and the process has no parent, then we treat it as executing the entry point rather than executing the actual arguments. I don't totally like this, and I would like a way to restrict this so that the sandbox can never enter this code path. As it's written right now, the first process that we execute could still come back and run exec and like re-exec itself. I would like to not have that be like a noticeably special code path. But so like one way this could happen is, one way this could happen is that in the emulated exec VE, if the task is stopped, well, if the stop task has no parent like that, and all the parameters are 0, then this might be a special system call, or it might just be a seg fault on a normal system call. Like if you called exec like this on a normal kernel, it would just give you like a, not a seg fault, but like a system call memory mapping error, like efault. I think we should try it. What's the easiest way to just try a system call? Could I just write a little separate Rust program? Yeah, I would like to know what that does normally. I think it would just return efault. Always helpful to read both the man pages and the kernel source for stuff like this. I think it's so funny that this is actually E2 big. I saw that in the kernel and I thought it was like a kernel internal code, but maybe it is actually external. Oh, can we do this? It's been a while since I made a new project. Version of syscall are we on? 0.23. I tried a couple of syscall crates, and this is the one I like the best so far. Okay, let's just make sure this runs as is. Okay. Right? This should, I mean, okay, we want the return value too. Oops. Oh. I always have the most trouble with delimiter errors. Usually when they're more complicated than that, though. Oh, Tuco. I want that to be signed, but thanks. That's right. I'm used to having to import the syscall numbers, but the syscall macro adds that automatically. Okay, is -14 efault? Yes, efault. So I think we can just do that, like in the emulator, detect this weird circumstance that we're using to load the very first process. Use that as a cue to ask the runtime whether we are in fact bootstrapping. And then the runtime would have something that it does only once per container, where it would allow the IPC server to say, yes, we are bootstrapping, and I will write the arguments into the address you gave me. Because from the tracee's point of view, this is going to look like you make a weird exec, and then you just disappear, and you're replaced by a different process. From the tracer's point of view, it's going to look like inside the emulation of exec, we have to make an IPC call to the runtime to get it to copy a parameter list into a specific place. It's really interesting to look at the Linux source code for exec to see how it does some of these, because it has the same problem where when you call exec, you need to somehow get the inputs into the process, right? Like, it's this whole like fundamental operating system thing of like, well, you're creating something out of nowhere. Where does the nowhere come, and what does it come from, and what is it full of? And so like you need to have a process that has some kind of state to it. And a lot of that is just coming out of your elf file headers. It gives you information about like at least where the entry point is, and then other things are like the address space layout is randomized usually, and a lot of the registers are set by the kernel to known values. But like none of that holds command line arguments, like they're too big. So they end up going on a string buffer in your stack. And the main function, like before your main is called in a C program, the startup code, part of what it's doing is making pointers to those stack buffers and passing them into the C code. But the actual data behind like argv and the environment, those are actually located on the stack, like at the very top of the stack. So doing a normal exec, the way this would work is that the loader has a stopped process that is trying to transmogrify from the process that called exec to the process that's being execed. And so at some point, it has these tracee virtual pointers representing the arguments and environment, and it just needs to relocate that data from one portion of the same address space to another portion of the same address space. So, and there's a bunch of tricky aspects of that, like, right, because like the memory is not going to stay mapped. Like maybe you need to copy it to a temporary location. I need to look closer at how Linux does this. I forget whether Linux copies the data or copies the mapping. Because there should be a way to unmap all the memory except for the pages around those arguments, and then remap those pages somewhere you'd like to keep them. But I don't know which approach I'll actually end up going with here. So I think the way this is going, the loader object is created with some set of parameters. And right now I've only got these two, but if you look at the Linux source code, you'll see that there are actually just like a bunch of different ways that you can get into the loader. And there are ways that the loader might end up recursively having to call itself, like if you're loading a script. So it's useful to have multiple ways of initializing a loader. So that's kind of what I was thinking with these two constructors. And I think this from entry point variant is just something that asks the IPC server from an entry point and faults otherwise. And then this execve is one that copies data from the same address space. So these will set up some kind of internal state in the loader indicating where the parameters come from, but then the actual copying happens like in the middle of the process of loading the binary. And then this do exec is our async function that just does all the rest of the work. And then exec does actually return. It just does not return to the same process. So do exec is going to mutate the state of the stopped process, changing its registers and deleting a bunch of memory mappings and making new memory mappings. And this return result is returning into a fairly different kind of like register set. Like, oh, we're not actually writing the registers here. Yeah, this just returns the value that will be written to the registers, but effectively the return value from these blocks ends up in the AX register. But on entry to a new process, there's still an AX register, and it contains 0, which is the success code. So it's sort of like exec is returning success, just into a different process. Oh gosh, and now we're at the loader. Oh gosh, this is also something I feel like I should get some help on from people who know Rust better than I do. There's this whole proliferation of lifetime annotations that I feel like I should stem at some point. I even have trouble remembering what each of these is. So see, like loader has Q, S, and T, stop task has Q and S, and then T is the mutable reference to the stopped task. And I think inside the stopped task, S is the stop itself, so like a mutable reference to the register set. And then Q is the task's event queue, so it has a lifetime that's the same as the lifetime of the entire task, roughly. I haven't been actually calling this a task lifetime because it is technically the lifetime of the event queue, and I'm not sure I want to make those two equivalent, but they're almost equivalent. So yeah, I think these are all legitimately separate lifetimes, because like this is roughly the entire length of the task. This is the length of the task being stopped, and this is the time during which we're running the loader, which are all distinct lifetimes. The loader only cares about this lifetime, and the others will always be larger, but I don't know if that lets us elide these lifetimes, because I think we have to write them, but that's definitely a part of Rust that I'm kind of fuzzy about, and I probably need to learn more about. Gosh, and then this is just all garbage code. This is where I'm just starting to like experiment with the environment here and try to see what I can do. So this part works, this big standard out that I'm doing. That's like the last thing we're doing before crashing. That command I'm running actually, so this cargo is the Rust build system tool. Cargo run is the same as just running my actual finished binary, assuming it doesn't need to be compiled. So that's similar to just saying target slash debug in this case, slash bandsox. So if I run that, that's the same as cargo run. If it compiled, which I guess it doesn't right now. Or no, it does. Those are just warnings. Sorry. Yeah, so it's the same as that at the end. I guess I get warnings each time, even if it's already compiled. That's nice. I didn't realize Rust did that. Anyway, so it wants a container image. So there's a bunch of images I can use for testing. I've been using like Alpine or BusyBox. If you just put some garbage here, it'll actually fail though, because it is downloading the container. I don't have good errors for this yet, but it's saying that it got a HTTP 1 or 401 from the registry. I think we can download Ubuntu also. It'll just take slightly longer. Oh, we do actually have logging for when it's doing the downloads. Usually it's running this out of cache because I've been using the same images, but yeah, if it's something I don't have cached, it'll actually download it. Oh, 2 goes back. 2 goes back. It's like running Ubuntu is not especially interesting though. One thing that I was using that as a test case for though is it is actually kind of a large distro image, and it should, like when I run this, it should still run pretty fast. Yeah, So it still runs pretty much instantly, even though the distro image is large. And that is specifically because it already has the decompressed version of the image cached. It saves that persistently. And it doesn't actually have to copy any of the data to create the in-memory file system. It just has to read a bunch of tar metadata, which I can do pretty fast. That actually required some kind of weird code, if I remember right. That is like a completely different part of the project that I've been working on recently. As you go way back up to the runtime, source, I'm like typing things wrong. That was in file system / tar, I think. Yeah. I actually went back and forth between a couple of different tar libraries before I ended up settling on the one that's actually just called tar. But the thing I want to do is actually slightly weird, because I don't want to extract the tar file. I just want to extract the metadata from the tar file. So I don't want to read the files at all. I want to completely skip the files, just read the headers and store the headers. And yeah, there was a way to do that with this tar library. It just required getting a little bit low level. But yeah, that's not too bad. You can create an archive cursor that walks over the archive, which in this case is just a block of in-memory data. And this map ref thing is a reference counted reference to an existing memory mapping. So yeah, this arc and map thing is actually what the ref uses inside. But the map ref reference counts that, but then it also contains a specific like subregion within that mapping. Like this is the object that I would love to find a good way of mapping into a file descriptor, the map ref. I feel like one way this could go is I could have a cache that takes map refs and turns them into like memfd files on demand. I just still don't like that because it requires copying an entire binary's worth of data at once, which could be a problem on large programs. So yeah, the Ubuntu eventually did run, and it looks the same as the other images because I'm not actually using any of the data from the image to run this current test. I'm pretty close. Like, once I get a little further in the loader, so like I'm in the loader first of all, which has just taken a lot of work to get to this point, but now that I have some code that is running, like I have async code which is running inside of exec, which is itself kind of nice. And I can make remote calls to a higher privileged server that I can get files from, and all of that works. Yeah, so in order to implement exec, one of the building blocks that I need is to be able to do some slightly higher level remote operations in the process that I'm tracing. So this includes things like executing a remote system call, not in the current process, but in the process I'm tracing. And it includes accessing memory in that process and passing file descriptors in and out of it. And I think the primitive I'm using to implement all of this is kind of building system calls in the traces register set and then running the system calls using ptrace. So I've got that slightly working, but it still needs a bunch of work. Yeah, so made it to exec with stop task. That is right here. Also, I'm waiting for somebody to complain about my printf debugging, but like this is the kind of low-level stuff where I don't know if I could find a better debugger than printf for some of this, actually. Like, I would like to be able to strace, but I can't strace because strace, you can't use ptrace while you're ptracing. And strace also uses ptrace. So I can't use that as a debugging tool. I can't use an actual debugger because that, of course, uses ptrace. Yeah, I mean, this is the kind of program where if you want a debugger, you basically have to write it yourself. So I might do that at some point later, but right now I feel pretty happy to have printf. Like, I mean, I'm not even joking about that. Like, Rust and its formatters actually make printf pretty nice. Like, I can just printf an entire stopped task, which is, that would be such a pain in C. And it doesn't involve like allocating a string, it just involves generating code that prints all the values. So because I'm doing unbuffered I/O, I'm sure that's turning into a bunch of tiny write system calls, but I mostly don't care about that because it's debugging. Yeah, so we made it to exec. We print out the register state, and then I've been trying to debug these remote system calls. So this is coming from remote syscall. I've got some printf debugging on the entry and out side of that. Just printing out the registers again. And then this, doing a big standard out, multiple strings even. Whose stack is this anyway? That is a string that I created up here. And I just grabbed some memory on the Tracy's stack kind of randomly. And I wrote that string into the Tracy's memory. And then I execute a syscall write on standard out with that string pointer. So this is actually executing one remote system call and then crashing. So the write works, but then I think I'm ending up in the wrong ptrace state after this. And so I'm trying to do basically the same thing again. Yeah, I was trying a different version of this earlier, which is still down here, which just has a loop that tries to call nanosleep. And I'm not actually filling in the time spec yet. My plan was to put a value in there, but I hadn't actually written the memwrite at that point. So this is just calling nanosleep with a garbage value, but I didn't even see this behaving the way I expected that to behave, so then I tried something like munmap or write. And write is nice because even if the state of the process is trash immediately after the system call, I can see that the system call itself worked. So we did the standard out, and then I'm checking the register state afterwards. Gosh, I feel like I don't know if I'm actually going to be able to debug this next part on the stream because I feel like I need to like get my head like really in the zone to do this part. But like the particular problem here is either that my tracer and Tracy are getting out of sync ptrace wise, which seems pretty easy to do given how the remote system calls work right now, or I thought it might have been something stack related, like maybe there's a mismatch in the stack frames, but I was doing this thing where I just completely save and restore the whole register set. So I save all the registers here, and then when I was looping down here to try testing multiple system calls, I tried just splatting the register set here, then doing a sleep, and this was still failing after one successful call. I think the behavior I was getting here is that I saw sleep sort of appear to work once, but it didn't have a valid time value, but the system call succeeded. I mean, the system call happened is really what I care about. But then after the first sleep system call happened, the second one returns with like an invalid system call number, which should not happen. Like something is in the wrong state, and so I'm trying to figure out like specifically what's going wrong. So yeah, there might be something else I'm doing wrong with the process state, but I'm pretty sure it's related to the ptracer. So that's what this is. This is another like really new file that does not have a lot of good code in it. It's mostly just like stuff I'm experimenting with. Yeah, I had some experiment here to print the maps. This was mostly just, oh gosh, it's 1 a.m. and I have this map file descriptor and I don't know if it's valid. I just want to print out the contents and see if it's valid. So like that's what this is doing. And it works, right? Like, can I demonstrate that? Oh yeah, so I have this print maps call. I'm just going to move this up so we can see it work. So now we should see made it to exec, and then we should see a dump of the process maps, and then it should start doing the system calls that mostly crash. Yeah, that's great. So made it to exec, stop task, there's the stop task dump, and then these are the maps inside of a result. And that looks pretty great. So the reason I wrote the sleep loop was half because I actually wanted remote system calls, and half because I just wanted the process to sleep so I could examine its state to see if anything else I'd written is actually working. Again, on the theme of this being kind of difficult to debug code, like I would like to be able to, for example, like have it sleep so I can just look at proc fd to see if the right files are open, but there isn't even an obvious way to make that process sleep. So, you know, I could make my asynchronous task sleep, but my asynchronous task executor system does not have a way to sleep, and I don't really want to add one since that's a lot of complexity that I don't actually need. Real task executors would have a priority queue of timers, and then they would use some kernel feature like a select or poll timeout or an alarm or something to ask the kernel to wake up the process on the soonest timeout. But I don't need any of that because I don't plan on having time be a thing that the sandbox or that the tracer has to interact with. It should really just be handling events from event sources, and it shouldn't ever have to pause or deal with real time. Like pausing would be bad actually because it's single threaded and it's an event loop. So if the tracer pauses, all the processes pause. That we could already do if we just did like a plain old sleep. If I wanted an asynchronous sleep that would let one task pause while not affecting other tasks, I still have to find a way to propagate that to some kind of time-based wake-up that is compatible with my wait ID loop. Because it's a wait ID loop and not a select or poll loop, it can't be a select or poll timeout. I don't remember if wait ID has timeouts. That would actually be a good thing to check. Yeah, so this wait ID is what we're usually sitting in the tracer, waiting for the kernel to give us events. Wait for a process to change state. Yeah, I don't think wait ID knows about time, so I need a separate timer. Can you do high resolution SIG alarms? So there's another old Unix feature kind of from the same era as asynchronous I/O signals. There are timer signals. You can just ask for an asynchronous signal when a timer expires. So normally these are super inconvenient, but the advantage of using a signal-based mechanism when I'm sitting in wait ID is that I can have it interrupt the wait ID. So that's something I didn't mention earlier, is that signals interrupt system calls when they occur. So when you're in a blocking system call and you get a signal, the system call will immediately return with a signal or with a return value saying it was interrupted, which you can check as soon as the signal returns. So yeah, if I needed asynchronous timers in the tracer, it seems like alarm would be one way to do it, but you notice that's in integer seconds, so it's not a very high resolution timer. You can only wait an integer number of seconds. It's kind of bad. But I think in the kernel this uses, yeah, so, okay, set iTimer. That's what we want. Oops. Yeah. This is definitely what we want if we end up needing asynchronous timers. This will be compatible with wait ID and it's high resolution. And I'm sure this is allowed inside Docker, but let's just double check. should just bookmark this or something. Yeah. Cool. So we could do that if we need to. So we've got print maps. Oh yeah, we were going to look closer at the maps. Yeah, so the specific maps are kind of neat too. So this should be a fairly empty process that, so like, one of the reasons I wanted to have a separate process for the sand application rather than just making it just like fork off from the main application and then try to strip itself down a little bit is I did actually want the kernel to be responsible for doing a real exec. There are some things that the kernel does when you do an exec that like reset the identity of the process. And so I wanted to be able to do that at least once between when the application like starts the sandbox and when I actually start running the emulated sandbox code. And I'm not going to be able to just arbitrarily exec later. So it's like I need the very first exec to kind of clean out my process as best as possible. And then anything that goes back in there has to be stuff that I know how to remove myself when I do an emulated exec. So having a real exec start out the process seems like a good security decision for that. So then this memfd pentacle sealed thing looks a little weird. This is actually the anonymous file that we created using memfd to run the sand process. And that's created using this other library that I'm using, which is just a very strange, weird little library. Crates. Yeah, the library that executes programs using memfd create. And like, I've already got like a system call layer I could use. Like, it wouldn't be hard to write this myself, but this was just such a cute little library that I couldn't not use this. So yeah, this is actually basically the same thing we're doing inside the sand process. I just couldn't use this library in that. And then, yeah, sealed command. This is what actually does the thing. So this is copying the program into the new file. So we could do this strategy basically to create anonymous file descriptors that refer to arbitrary stuff from our virtual file system. It's just that every time we did that, we would have to copy the contents. Question from Twitch. Someone's asking why the no standard. Yeah, I went into a little detail on that earlier, but it's mostly because I want to be writing code that's operating directly on system calls. And so, like, no standard does a couple of things. It means that it kind of strips out the parts of Rust that require memory allocation and the parts of Rust that interact with the operating system, and then you can kind of opt back into the memory allocation if you want. So the memory allocation is not the part that's a problem. I'm avoiding dynamic memory in the tracer mostly because it seems like a good decision for reliability and complexity reasons rather than because I can't do it. But the no standard library thing is mostly because I don't want to be using the standard C library. And that's for two reasons. One is for size, because it's easier to have like a small binary if I'm not like linking in an entire static libc if I'm just making system calls. But like the maybe more important reason is that I actually need to be fairly cautious about which specific system calls I'm making, because this is all designed to operate inside of a restrictive setcomp profile and a ptrace tracer. So I care a lot about system calls, and no standard is a good way to let me just drop down to raw system calls for every single thing. I was also happy to realize that the way that the proc files work, if you have a file descriptor open to proc whatever maps, the kernel will refresh that to a current representation of the process's current maps anytime you do a seek. So you can just keep the file open, you can seek and read, and then get a complete copy of the maps. I mean, you can seek and do multiple reads if you don't want to read them all in one buffer too. I was looking at that, and the kernel doesn't actually have a fixed size buffer for any of that, nor do they dynamically allocate. I think they're actually filling in your read buffer based on the kernel's data structures directly using some code specific to the proc file system. But I could be misunderstanding what's going on there because I didn't look in a lot of detail. But that seems kind of nice, and I don't know, like one way the unmapper could work, for example, is I could just have a loop that reads the maps file after seeking to determine whatever the next map is, and then unmaps that, and then just repeats the process, so that I don't need any kind of buffers that are limiting the total number of maps that it supports. Gosh, well, this has been like 5 hours of talking and not as much debugging, but I feel like that was a useful data dump at least, and hopefully some folks enjoyed it. I don't know if I have the energy to like launch into a serious debugging session at this point, or if I should probably just like wrap this up and try to eat a snack or something before diving further into this. I feel like the next step here is to just do a deeper dive into what specifically is going on with this remote system call. When I was setting up the stream, I was imagining that that involved just doing a bunch more like printf debugging and making experiments to see what's actually going on. But now that I've been talking about this and thinking about this a little bit in the background, I'm realizing that the fundamental problem here is that I don't have a complete enough understanding of specifically what this thing is. ptrace syscall. This isn't what it's actually called. That's my wrapper for it. But ptrace syscall. Yeah. This is important, and I need to understand it more carefully. This is an operation where you're asking ptrace to run the process that you're tracing until the next entry or exit from a system call. So I need to understand better how exactly that interacts with setcomp tracing, because I'm using these two features together, and it seems like the way they interact might be a little weird. Because mostly what I'm using ptrace for is to trace instances where I'm trapping specific system calls. And actually, I don't know if I went into this specifically, but that is something I'm specifically asking for in the setcomp policy here. So I'm setting up setcomp, and yeah, some of these are allowed, but a lot of the system calls have this setcomp ret trace. So that's specifically asking the kernel to, when the system call happens, to trap the process right there and give me access in via ptrace. So it seems like that is very similar to what happens when ptrace stops at the entry to a system call during ptrace syscall. And I've been assuming that probably what happens is that the setcomp trace is similar to that entry, and then running ptrace syscall again, I'm actually allowing the syscall to execute and then getting control back when the system call returns. And I think the problem at that point is that I don't know what to do to get the process back into the right state, and I'm just not doing that correctly. And I think what's going on is that when I try to run an additional system call, it's actually restarting the process and letting it execute code until the next system call, which is just going to be something garbage. And in fact, once I unmap the process's memory, that would just immediately segfault. So I was trying to unmap memory actually partly so that I could try that. Like I wanted to, as part of working on system call remoting, I wanted to try unmapping all the memory and then making sure that I can invoke remote system calls in a completely empty process address space. That was like an intermediate goal I wanted to reach. But in just trying to get that working, I couldn't get my mem unmap to work reliably. So I also need to get more familiar with like what specifically unmap allows me to do. Because it'd be cool if, for example, you could just unmap the entire address space in one call. But I tried that and it doesn't seem to work, and I'm not sure why. So I need to look more in detail about where that's failing and probably read some more kernel source code. Let's have some cat time. There will definitely be some more reading kernel source code in my future, though. The chapstick is still on the floor. Tuco didn't want it. He just wanted to push it off the table and bite it. Or maybe he wants it, but he's too comfortable up here to get it. That seems likely. Oh, you want head scratches? Gosh, it's funny that the servo thing was called jail. I had no idea. I specifically chose a non-carceral name for my project. Like, we already got enough code being locked up. This isn't a jail. It's just like, you know, how you put socks on when you're playing in a band. It's exactly like that. Tuco is shedding all over me now. It's great. I'm also happy to like answer any questions if folks have specific topics before I wrap this up. I know a lot of this was probably just like a whirlwind of weird low-level stuff, but I'm also happy to like ask or answer like questions at a different level of detail.
What did you mean in the beginning when you said something like, oh no, not another ptrace jail?
Oh, I just feel like the thing that I'm doing is something that's been done a lot, but not quite in the same way. Like, I don't know who's doing it these days, though. Like, ptrace is just like a semi-esoteric Unix feature that people have done a lot of weird things with over the years. And I don't know. I was slightly joking when I said that, because like I'm still excited about the thing, even though it might be a slightly weird idea. But yeah, I guess what I mean by ptrace jail is just that this is like a general type of software where you have a process that you want to try to restrict from doing certain types of things, and you use ptrace as a kernel mechanism to implement that restriction. And I think where it often falls down is because of that time of check, time of use vulnerability that exists if you're trying to use strings. So if you're trying to do the thing where you ptrace the process and then check to see if it's opening a good file or an evil file, and it looks like it's opening a good file, it could just swap out that pointer for an evil file like right after you let it run. So that's never reliable. But like there are other ways of using ptrace that are reliable, like debuggers and like user mode Linux. I don't know if I would call that the most reliable thing, but that's what they used also. I think ptrace is weird. It's like a weird corner of Linux that's had some like weird bugs in it in the past. But yeah, I mean, it's also been around for a lot longer than some of the kernel features people are using pretty regularly. It's also historically something that I think people assume is going to be both slow and hard to get right. And I feel like my ticket out of that is that I'm kind of adopting two different code paths where I/O operations directly to file descriptors go directly to the real kernel, so they're not slow, and other operations like open and exec that wouldn't be possible to get right by passing them to the real kernel, I'm doing them the kind of slower emulated way, but doing it with a fairly thorough emulation that I intend to be a solid kind of security architecture. So, I mean, security is always a process rather than just something you design into a thing once, but this feels like an architecture that can have a sort of reasonable level of complexity for the things that I want to do in the near term, and that can be possible to maintain in a secure way. Oh, there's a comment from Twitch that I have a chair for my cat too. Actually, I just brought in, this isn't even a chair. This is like I mean, I guess it's a chair for him, but this is actually a stool with a cardboard cube on top of it. I've gotten Tuco various pieces of furniture over the years, but this weird little cardboard thing is one of his favorites. His other favorites right now are these tall cat trees. I have two of them, and I think he likes them because he can like stretch out really far and scratch like above his head on them, and he can also jump on top of them and use them as perches. That's an interesting question. Jedi Punk is asking what I think of my trackball and why is it the best pointing interface available right now. Wink. Yeah, apparently their family uses trackballs a lot too. Ah, man, I feel like I've used a bunch of different pointing devices over the years. There was even a period of time when I was one of those extremely weird nerds who used a touchpad on a desktop computer. But I like the trackball for two reasons. One is that it doesn't hurt my hand as much as mice. And the other reason is I find that for doing like CAD and design kind of work, it makes it really easy to separate the clicking and the positioning parts. So you can position the cursor and then clicking without moving it even a pixel. And I like that for a lot of stuff. Oh yeah, Tuco is a polydactyl cat. He has the extra fingers and toes. And lots of purrs. So purring. Yeah, I actually got two of these same trackballs because I wanted one on my streaming setup and one on my like editing desktop. They're pretty nice. I have mixed feelings about the wirelessness of it since I kind of prefer the reliability of wired input devices, but I think at the time I bought this, they didn't have a wired version. Oh yeah, nice to see folks who we haven't crossed paths with in a while. Like, yeah, I feel like I went through a period of time not really being sure what is worth contributing to the world in video format in 2020, but now I'm kind of just in project zone and like, fuck it, I'll just stream, But it also feels like something that's maybe more interesting to share than just maybe some of the stuff I was working on before. Oh, did they totally stop making wired versions of this trackball? That's a pain. Yeah, I would almost modify this one to be wired, because I like the form factor. Although, it's still not perfect. Like, I've had more trouble as these trackballs have gotten older with them getting kind of more sticky. Maybe there's just a different way I should be cleaning them. I usually just clean the trackball and the sensor with just like a cloth or something, or just like wipe my t-shirt on it, but maybe there's something I should use to keep them from getting sticky or something. Because it's just this annoying bit of like stiction where the rotation isn't quite as smooth as you want it to be. Maybe I just have to take it apart and clean it more thoroughly. It's like you had one job with the precise positioning, right? The stiction is pretty annoying. But other than that, I'm pretty happy with that particular object. I also tried a couple of other little... Oh, somebody a while ago recommended me this... or was it a recommendation? I could be remembering this wrong. I thought somebody on the stream recommended this like weird little wired trackball, and I picked up one of them. And that was actually kind of nice. Not as like a everyday driver though, but just as like a tiny trackball that I can keep near the streaming setup to poke at things. But yeah, since then I've switched strategies, and now I just have these and I guess it's like slightly off screen, but I've got like a switcher up here on this keyboard. Oh, I can just barely see it. This thing, which I built like last year, and there's some video of me building that. I should post more video of me building that actually, because I took and even edited a bunch of video that I haven't really shared that feels incomplete, but is probably just worth throwing up there. Aw. That's funny. From the Twitch chat, their 7-year-old has a they have a left-handed 7-year-old who is always having trouble with the trackball with the same like cleaning and stickiness issue. Yeah. I'm actually left-handed also, but I've never had much luck using left-handed input devices. I'm not really sure why that is. But I do a lot of things with my left hand, but mousing is not one of them. I'm probably kind of weird. I've seen the like symmetric versions of these though, and those seem pretty cool. I should probably give one of those another try. Oops. Turning off the wrong channel. All right. Oh, cool. I guess I'm not the only lefty who mouses with the right hand around here. That's neat. Oh, gosh. Well, this is seeming like maybe a pretty good time to wrap things up for now before they just drag on unnecessarily. But I'll try to keep doing these relatively frequently, and I feel like this one I just did a big coding binge to get all this stuff out of my head, and now I'm like telling you all about it. But maybe there's more room to do some more like interactive development. I'm trying to keep this from being too boring though, because I know these things can get a little dry if I'm just staring at an editor the whole time. Well, cool. Thanks so much for joining. And special thanks to all my patrons who contribute to my Patreon and keep this going. That's really like how I can focus on doing this more than so many other things right now and keep on my electric bill and my health insurance. So I appreciate that a lot. And as always, if you have suggestions for like what you would like to see more of or less of, I'm all ears. I'm on a few of the social things. You can always just like drop by chat on the stream when I'm here, but I'm also on Twitter at Scanlime or Scanlime Live. Scanlime Live is mostly a notification bot. I've been bad at checking the notifications there in the past, which I should probably fix, but there are some Twitters that you might be interested in, like the one I recommend everybody follow is actually my cat. He's got a Twitter account that's all pictures. No, none of that pesky text. Just oh, it's got video too. I mostly have my video autoplay disabled on Twitter, but I'm not logged in here. But yeah, Scanlime Live is just notifications. So yeah, this has a bot. Oh, it just posted this great picture of my butt. Cool. Yeah, so this bot posts when I start streaming, and every couple hours while I'm streaming, so it won't spam you too badly, but every so often it just gives you a screenshot of what's going on. And then my actual weird self is over here if you want that for some reason. And this is very different depending on what mood I'm in, but right now it's been mostly just kind of project stuff. So, 'tis the internet. And the computering. And the green screen. It's looking a little surreal with the flickering around the edges. Alright, well, thanks to everyone, and have a good night. I'll see you next time, and until then, happy hacking.